Okay, I think it's time. Hello, everyone. Let's give it one more minute to allow people to get in the room, and then we give it a start. Okay, let's start. So my name is Cecilia Arigui. I'm one of the organizers of the BioCreative Challenge, and welcome for this BioCreative 7th Challenge Evaluation Workshop. It has been already started in 2004. It has been a long while been running this series of workshops. I'm going to give you this very short intro, basically to give you some general guidelines, and also to go over the program today and what exciting things are happening. So in terms of general guidelines, I would appreciate everybody. I know attendees, when you come in, you're muted, but at some point we might allow you to speak if you raise your hand in the discussion session. So in that time, make sure that you are muted when you finish speaking. And the same for the panelists, make sure you're muted unless you are speaking. Also, we are going to use the question and answer. So try to identify in your menu bar for the Zoom webinar, the Q&A box. That's where we're going to post, people will post their questions. And in the chatting box, on the other hand, will be for all other comments on either if you have some issue or if you want to say something to some participant. However, we are opening this for communication, but we expect respectful behavior towards all attendees. So we will not tolerate any harassment or intimidation of any person or any harmful comment. So please be responsible. Another thing, if you have any technical issues, you can contact either indicating in the chat box or sending an email to BioCreative Challenge. Let me go over the next slide. So we have now the proceedings available. You can take a picture, scan this QR code to access the proceedings, or you can go to the BioCreative website and you have the link there. Also, we will have a poster session in the meeting where we have flash talks with some of the posters selected. But if you want to see the complete list this is the presentations, which are amazing. You can go to this site. Also, everything is accessible from the the BioCreative website. So, and if you want to tweet anything, you can use the hashtag BioCreative. In terms of the scientific program, today we have a great program. We have first all the overview and results from the track regarding called NLM-Chem track, which is chaired by Zhiyong Liu from NCBI. After this session, we will have a short break of 20 minutes, and then we have an amazing keynote speaker, Joshua Denny from NIH, who is from the All of Us research program. And after that, we will have the overview and results of the track 3, which was the automatic extraction of medications named in tweets, which is chaired by Davy Weissenbacher. On Tuesday, remember, tomorrow we start half hour earlier, so just bear that in mind. There have been a lot of participants of the drug prod track, so we needed to allow more time for the presentations. This session will be chaired by Antonio Miranda and Martin Kralinger from Barcelona Supercomputing Center. There they will have the break and the poster flash talks. This is chaired by Resarta, who's going to play the posters, the talks. And in this session, the posters presenters will be available in the Q&A for responding questions. And after that, we will have a great panel with about challenges in mining adverse drug reactions. And we expect a very fruitful discussion there, chaired by Martin and Lynette Hirschman. And the third day, we have everything in the morning and afternoon about COVID-19. One has to do the results, the overview and results for the lead COVID track for multi-label topic classification for COVID-19 literature annotation, which is chaired by Resarta Islama from NLM. And also after the break, we have the interactive part of the BioCreative, which is the presentation of the overview and the different systems that provide a demo for users to test and provide feedback on their system. And most importantly, at the very end, we have a general discussion. It is really important, and I encourage you to attend to this discussion, because you really can have a great input here if you provide your insight into what BioCreative means to you, how we can advance BioCreative, how we perceive this, what can we do for you or the community. So I would like to mention this has been an amazing group working the full year to bring you this workshop, or this very time-intensive, labor-intensive activity. A lot of people, and also give a special thank for the people who have been working to help making this event, like Julie Coward and Emily Oldham from University of Delaware. They were assisting with BioCreative website and the proceedings. Christopher Martin is the media services at University of Delaware, who is helping on the technical side for this workshop. Antonio Miranda Escalada, who has been setting up the YouTube channel for the poster sessions and other things. And also I wanted to thank the International Society for Biocuration for their members being such a great community that always eager to help us with testing systems. And again, all users who took the time for the busy schedule to participate in any way, not only in interactive tracks, but helping with annotation guidelines and everything related to the tracks. So no more I don't want to go over. I just want to pass this to Zhiyong Lu, who's chairing the first session. I hope you enjoy this meeting. Go ahead.
All right, good morning, or good afternoon, or good evening, depending on where you are. I'd just like to, my name is Zhiyong Lu, a senior investigator at NCBI NIH, as well as a co-organizer of the Biocreative Challenge. And I'd like to extend a welcome to all of you this morning, and I'll be chairing the first two sessions this morning. So the first session is about NLM-Chem track, full text chemical identification and indexing in PubMed articles. So in this track, we have a total of 5 talks. We start with the overview talk for 25 minutes with 5 minutes Q&A, and then followed up by 4 team talks, which were selected based on their methods as well as the performance they achieved. Each team talk will have 9 minutes talk and then 1 or 2 minutes for Q&A. So to help the speakers to keep track of time, I set up timers for you, and the first time you hear the ring, it means that you have 2 more minutes before the end of your talk, and the second time you hear the ring means your time is really up for your talk. And for attendees, I strongly suggest you, because we're running talks after talk, and this is a virtual platform, I strongly encourage you to post your questions during the Q&A, so that each speaker, if they don't have enough time to address all the questions, they can also answer your questions after their talk. So without further ado, let me introduce the first talk, the overview talk by my colleague Rizata Islam and Robert Lehman. The title of the talk is Overview of the NLM Track, Full Text Chemical Identification and Indexing in PubMed Articles.
Hi, everyone. I would like to welcome you all to the meeting for Track 2 and NLM-Chem. I know we have in attendance the team participants. Glad to have you here. Biocurators, I'm glad to see you here. And I think we also have some teams who registered for the track, but were not able to make the deadline. Please feel free to get in touch with us if you wish to continue the conversation later. As Cecilia said, Biocreative is a series of challenges started in 2004, and its goal has been and still is to bring together this diverse community of researchers. We all have somewhat different backgrounds, but joined in our aim to solve real-world biological problems. Identifying chemicals in biomedical text has been addressed in several biocreative challenges in different ways, starting with ChemDNER and CTD tasks in 2013. In particular, ChemDNER requested the recognition of chemicals in the abstracts and titles of PubMed articles. This was continued in Biocreative 5, where ChemDNER was extended to abstracts and titles of patents, as well as PubMed abstracts, and the CDR task focused on identification of relations between chemicals and diseases in PubMed abstracts. Then we have ChemProt in Biocreative 6, which introduced the recognition of relations between chemicals and proteins, and this continues in DrugProt, of which we will be hearing tomorrow. NLM-Chem track extends the chemical recognition to full text articles, and I'll talk about this in a couple more slides. We link the chemical mentions to the MeSH vocabulary, providing normalization, which via UMLS can be mapped to other ontologies, and also allowing for links to PubMed articles and other resources at the National Library of Medicine, and explores the selection of chemical terms as topic terms for the given articles, which is another important way of linking the literature together And we'll talk about this again. So envision the NLM-Chem track as two separate tasks, the chemical identification and chemical indexing, but both of them will be tested on recently published full text articles, because this is the real challenge, utilizing and leveraging what we know and what we have seen so far in the new space that we have not seen yet. For chemical identification, it can even be divided into two subtasks, if you will, for the mention recognition part and the entity linking via mesh. The chemical indexing focuses on predicting which chemicals mentioned in the article should be topic terms for that article, which means which should be listed as medical subject heading terms for the document in the National Library of Medicine indexing. While for many people, they can think that chemical identification is a problem that may concern a small community of people, it does prevail in the biocreative challenges, and we're still working on it. And the reason is because it has a critical importance. Why is it important to identify chemicals? Well, we know that they are one of the most searched entities in PubMed, as it's also illustrated here in the image on the left of your screen. However, and they do appear throughout the biomedical research literature, not only on studies about chemistry, but they are important for health and medicine, biology, pharmacology, drug research. Identifying biomedical entities correctly helps not only the users who search for the right article via the search box, but also makes it possible to group articles of similar topics together, therefore making it possible to extract that knowledge for further research. And this was especially important during the COVID-19 pandemic. And this is one recent article. The importance, during COVID-19, the importance of identified chemicals became even more pronounced. So in that sense, NLM-Chem track is quite literally very timely. The highlighted chemicals here are biomedical entities, and chemicals are shown in green. Here's a depiction of, in PubMed, for that same chemical that we saw in that article, and the distribution of articles containing that chemical since 1946. I would like to draw your attention here. We have an unexpected number of articles suddenly mentioning this very chemical. But that's not the whole picture. Let's look at this other chemical. Previously, we have only a handful of articles mentioning this chemical before. However, suddenly this chemical is dominating the landscape. Which brings us to indexing. Finding these chemicals in text is one thing. However, collecting the articles which contain crucial information related to the given chemical is another. And as you see here, not all articles mentioning a given chemical are indexed with that term. That's because indexing gives a different meaning to the found substance. It signifies that the article in question contains some significant information related to the chemistry, interactions, or clinical significance of that substance. Let me illustrate. This is again the same chemical, and this is the PubChem page for that. You see the chemical structure, you see the molecular formula. Of course, the naming conventions, they have a standard name for this chemical, but this is how it appears in biomedical literature. Chemical recognition is difficult because authors do not use the chemical naming standards, and therefore we find innumerable name variants for a given chemical substance in the literature, which has resulted in a long list of known synonyms and also synonyms for which have not been linked yet. Therefore, we need the automated methods that are able to recognize these. The mention of chemicals is difficult to identify because it may not refer to one chemical only. It may refer to mixtures of chemicals, or it could be in ambiguous terms, or it could be mentioning a chemical which we still have not cataloged yet. So that's one issue, the sheer number and diversity of all different names that a substance could have. Now let's look at the problem from another perspective, and that is the difference when we're looking at title and abstract and when we're looking at the full text. This slide shows at the time our state-of-the-art chemical recognition program, Tiger-1, and the performance which we were very proud of on identifying chemicals, mentions, and linking to mesh ID on the title and abstract data set. And running that same model on the NLM-Chem full text testing data set gave us a hurtful experience. We saw a significant drop in performance. Retraining that algorithm, when we augment the previous data set with the full text training data set, we see that we can improve the performance, and we can work more with the algorithm and with the data set to increase its performance to the inter-annotator agreement standard. With this work, we actually verified something that biocurators have known all along. It is the article's full text that tells the real picture. Therefore, automated methods should be trained and be capable of handling full text. And this is why it's an objective for the NLM-Chem track. So we want to foster development for accurate chemical identification in new articles, because we want to be prepared to be able to handle the changes in the landscape of chemicals. We want to improve chemical identification in full text, assist chemical indexing, which in turn helps improving the linkage between chemical names, PubMed, other databases, therefore fostering deeper understanding of chemical properties, interactions, and so on. And with this track, we also provide a manually curated corpus of comprehensively annotated with chemical entities and chemical index with chemical substances. Let me talk a little bit about the Trig data set. It's better, we think of it in three distinguished parts. We have a corpus which with a full text corpus annotated with chemicals. The 150 full text articles were published before as the NLM-Chem dataset. These were augmented with 50 full text articles, which served as the chemical identification task testing dataset. These were recently published articles, and I'll talk about the selection method and how we made them fit the NLM-Chem. Because we want to be able to apply this to the whole biomedical literature space, and including not only journal articles, but patents as well, and as other resources, we provided as supporting training data the previous corpora from previous BioCreative on chemicals. And the last piece that we provide as Trig data set is the chemical indexing testing data. Here's an overview of how these data sets, like the main categories. We see that the full text data set is richer. It has more chemicals. It has more chemicals per article. But they do relate to each other and complementing the space of chemicals in the biomedical literature, as we know. This is how they overlap on mentions of chemical names, on chemical identifiers, annotations, and the indexing terms. As we have equipped the previous data sets with the indexing terms of all their respective articles, so they can be used as training data for the indexing task as well. And this is an example of how the two tasks relate to each other, but at the same time, they are also different illustrating the annotation of chemicals and the indexed chemical substances. I touched a little bit here earlier on the testing data selection. The goal, of course, so there's two things. There's factors that we can control for, and there's factors which we cannot control for. If we want, one of our goals is to develop methods that can adequately be robust with the new published articles, so that they are able to perform adequately even on research publications that we have not seen before, then we have to be aware that the vocabulary and the exact set of entities in the set that we have not seen in the future set, we were not able to predict that. That changes over time. But there are things which can control for. So the articles in the data set, in the testing data set, complement the training data because they are chemical articles, they fit the language model, they fit the same distribution of chemicals similar to the ones in the training data set, that fits the distribution of other biomedical entities. So they work together as a coherent corpus. We've employed two different evaluation techniques. The strict ones, I don't think this needs much description to this audience. It's your standard recall, precision, and depth measures measurements. It's your typical evaluation where you require that what is predicted matches exactly to what is annotated in the data set. And this is the same for whether we are looking for chemical mentions or whether we are comparing the predicted identifiers. For the approximate measure, the evaluation on chemical mentions and the evaluation on chemical identifiers is a little bit different. For the NER evaluation, we require that a predicted mention, if a predicted mention overlapped with a gold standard annotation, then we will take that into account. Of course, the tool that we sent to all the teams took into account that you cannot, like the extreme cases when one can return the whole full text article as an annotation prediction. So that's not counted for. Reasonable overlap between the predicted mention and the gold standard mention. About the approximate identifier evaluation, we used the same method proposed in the BioAsk challenges, where they take into account the mesh hierarchy and augmented the reference and the predicted set with the ancestor of the term in an ontology, and use the best to the lowest common ancestor. Regarding the benchmark, for the chemical identification task, we used as benchmark our newest tool on NLM-Chem, which is composed of two parts on chemical entity recognition and chemical entity normalization. And for more details of this algorithm, I refer you to our paper. It is a fairly sophisticated method, and we tried to help all the task participants by giving them enough code to get started on the chemical entity recognition part. For the chemical indexing task, however, as a baseline, we simply used a simple rule. We counted all the mesh identifiers predicted in the title and abstract, and presented those as candidate for indexing. So it provides a better recall, but it's the precision is not so good. And these are the baseline for the chemical identification task. You see the chemical entity recognition scores and the chemical entity normalization scores. Where when Robert takes over, he will compare this with how the teams did. And this is the baseline for the chemical indexing task. As you see, we do have a reasonable recall at lower precision. So a track timeline, we have worked for the good amount of 2021 on this task. The spring was a very busy time for us and the 12 NLM expert annotators who worked on annotating the chemical identification task test set. The selection of articles was a time-consuming process, making sure that the articles that we were selecting as testing complemented the articles that we had in the training data. And now I will pass on to Robert, who will talk to you about the teams that participated and the results.
Excellent, thank you, Rosarta. I'll go ahead and share my screen now. Okay, there we are. So let's go ahead and discuss the team participation and the results for each of the tasks. We had a total of 88 submissions from 17 teams. Not all of those were valid. We had a total of 74 submissions that were valid. We allowed the teams to submit up to 5 official submissions per task. We had a robust participation in the identification task with 56 submissions from 15 teams. Participation in the indexing task was significantly lower. We did allow teams to send results after the deadline. We marked those as unofficial. Note that some of the teams sent both official and unofficial results, so the total is that these aren't quite in the totals. We can already see that the indexing task is a lot more difficult with the reduction in submissions, and also that so many of the submissions were unofficial. Here are the results for the named entity recognition part of the identification task. This only shows the run with the highest strict F score for each of the teams. For the full results, please see the proceedings paper. The benchmark system set a high standard. This was a transformer model with BioBERT, but 77% of the submissions beat this benchmark. Here are the normalization results for the identification task, again showing only the run with the highest strict F score for each team. The scores are significantly lower overall with a greater differentiation. The benchmark set a high standard again, but 28% of the teams of the submissions achieved higher strict F score. Looking at the NER results overall, perhaps some perspective is in order. Team rankings are important, but tend to obscure the fact that the practical differences are a little less. Also note that so many of the teams had high scores. No one team dominated any particular area in this precision recall space. Our benchmark is the blue X, highlighted here with the blue circle. And we're now going to zoom in to discuss methods in this cluster. The first method to highlight is the clear effectiveness of using ensemble models. Second, it's worth mentioning a couple of the teams. Team 128 augmented their training sets with synthetic data, and Team 139 did the same with a different method, but also fine-tuned their models on the additional data sets that we provided, then again on the NLM-Chem data. Most importantly, while many teams use deep learning transformer models like BioBERT, PubMed BERT, and others that use a biomedical vocabulary have higher performance on NLM-Chem. Moving on to the normalization performance, we can see all the submissions to the identification task in strict normalization F score descending. You can see the scores are a bit lower. While strong NER score is necessary for a high normalization score, it's not sufficient. And in fact, the submission for the highest that achieved the highest normalization score was ranked 15th in the NER scores. Looking at the methods, direct matching straight to mesh provides high precision. It's a great place to start. But teams typically paired this with an additional approach, and any of these approaches can be effective, especially in combination. I'd like to highlight one in particular, where using biomedical word embeddings to convert the mentions and the names to dense vectors seems to be very effective at producing high recall. All of the submissions in orange here are ones that use this approach. Notably, Team 157 trained a model specifically to do that for this task, and their 5 submissions achieved the highest 5 recall values for this task. Moving on to indexing. These are the submissions with the highest strict F score for each participating team. This task was exceptionally challenging. You can see that the highest F scores are less than 0.5. The baseline system returned the set of chemicals found in the title and abstract. 44% of the submissions improved on that performance. While the task itself is certainly difficult, it's worth mentioning that the timeline probably contributed. The deadlines for each of the tasks were the same, and then after the deadline, there really wasn't ample time either. To understand the difficulty of this task, we should note first that using the normalization results for indexing is very strongly pipelined, and so you require to start off with very good normalization results. Beyond that, we might consider what the human indexers would use in order to decide if a term should be indexed. For example, the document structure. Terms mentioned in important locations like the abstract or the captions are more likely to be a main topic. Second, terms mentioned more frequently are more likely to be a main topic. And third, some terms are more or less likely to be indexed in and of themselves. And finally, some inference is sometimes needed. All of these aspects can contribute. Well, in summary, the contributions of the task are as follows. We have the NLM-Chem 200 corpus, 200 full text articles, doubly annotated by 12 NLM indexers, including a new testing set with 50 recently published articles, and the chemical indexing testing data set with 1,387 full text articles. For the identification task, we had 56 submissions from 15 teams, 77% improved on the benchmark for NER, and 28% for normalization. For the indexing task, we had 18 submissions from 4 teams. This was significantly more challenging, but the participants identified several aspects which should support future attempts to address the task. We realize that indexing is very hard, but we are working towards having the NLM indexers do some manual validation of the predicted indexing task results to see if they pass human consensus. We'd like to thank our PI, Zhiyong Liu, and the many colleagues who have supported our work on NLM-Chem, and especially the expert annotation team at the NLM indexers. I'd like to give a special thanks to the participants who've stuck with this task and worked so hard over so many months. The NLM-Chem task is available. We encourage you to download it and use it, spread the word. And there are open positions in the BioNLP group at NCBI. Please contact our PI, Zhiyong Liu, if you are interested. Thank you. Are there any questions?
Thank you, Robert and Rizanta, for your great presentation. I see in the Q&A there is one question, and this question is specifically for Robert. Why is approximate score, I guess, lower than the strict measures? Could you say something about the evaluation approach?
Absolutely. The approximate score might be lower than the strict measures for the specifically for the normalization task. And in that case, the approximate measures, the way it works is it adds additional nodes to attempt to identify paths between the reference and the predicted values, and sometimes those nodes are not the paths that are added end up reducing the score. To get a better answer for that, I think we're going to need to look a little bit more carefully at some specific cases, and I'm not prepared to do that at the moment.
I brought up the screen, Robert. Maybe
thank you. Thank you, Caesar. Yes. Thank you, Roman, for the question. Yes. So yeah, the lowest common ancestor F measure is one that I'm not aware of it being used in normalization previously. Certainly, it's been used for the BioAsk task, it turns out it didn't add a whole lot of information to be able to provide any difference to the rankings, and so we wanted to use it, wanted to see if it was something that could be helpful, but it ended up, looks like we're going to need to do some more analysis, or perhaps maybe methods that use the mesh hierarchy more might make this useful.
All right, thank you, Robert. And if any other questions, please feel free to post in the Q&A, and we will. And there's one other question I just posted. I think I'll let you to answer quickly if you have a quick answer. What is the current thinking strategy between MESH and PubChem? MESH has a direct lag time in PubMed, few months.
I can answer that. So these are different resources, right? MESH has definitely has a direct lag time, and this is related because it's manual annotation. Indexers at the Library of Medicine manually review the articles to make sure that the medical subject headings correctly identify that article and identify the topics of classify that article against the whole medical literature. For PubChem, PubChem has a different objective. PubChem has the objective of collecting all the information that is available for a chemical. So MESH is a part of PubChem, but PubChem combines together many other resources. So MESH is a part of PubChem.
All right, thank you, Rosetta. Again, people can continue to post your questions on the Q&A, but we will move on to the team presentations. Our first team presenter will be Joao Silva from University of Aveiro, and his presentation will be chemical detection and indexing in PubMed full text articles using deep learning and rule-based methods.
Hello, everyone. Do you have the video to play?
No, this is a live presentation. So are you ready to present this live?
I was asked to submit a video presentation. I was not told to make a live presentation. If you can play my video presentation, which respects the nine minute period.
Yeah, we can do that. Although
I can do that, Zhiyong. Do you want
okay,
me
thank
to
you,
do that?
Rizarta.
I can do that.
Because I don't have the slides prepared here right now. So
no problem.
I believe that watching the video would be best for all the
Sure.
attendees.
Let me just share my screen. I'll do that.
Okay, thank you very much.
Can people see my screen? Okay, great.
Hello, everyone. My name is Rafiki Silva, and I'll be presenting our group participation in the NLM-Chem challenge track. High-quality information retrieval depends on quality annotated information, and the major problem is that curated annotations rely on manual annotation procedures. With the current rate at which new research is being published, we are witnessing for the first time in history a scientific information overload where researchers cannot keep up with the rate at which data is being created. Considering this, automatic annotation is inevitable and is the only solution capable of dealing with this scalability problem. While previous challenges focused on abstracts, this track took a step further and focused on full research articles, which contain much more information and are more complex to process. There are two main tasks in this challenge, namely chemical identification and chemical indexing. but we decided to split the first task in two different subtasks addressing chemical recognition and normalization separately, thus resulting in 3 separate subtasks. Aside
We lost audio, Zhiyong.
Yeah, we're not hearing the recording for the video, Zhiyong.
classified tokens according to the biotagging schema. The process of feeding PubMed Word with text sequences was accomplished using the technique which will be described in the next slide. In an attempt to explore contextualization as much as possible, we set input size to 512 tokens, but only forwarded the 256 central tokens for classification, whereas the 128 tokens at both ends were only used for providing context. As we know that each passage from the full text can have several sentences or paragraphs, and these can greatly vary in length, instead of performing sentence splitting, we decided to sequentially shift the sequence by 256 tokens and feed it to the model. This approach has the advantage of being simpler, whilst keeping the additional left and right context of the sequence. This table presents the results of our 5 submitted runs. Note that test in selected epoch corresponds to the test partition in the training dataset. Run 4, which obtained the best results, corresponded to a configuration where the model was firstly trained on all datasets and then fine-tuned on the NLM-Chem dataset. In this configuration, the last layer of Word was also trained in the process. For normalizing detected entities, we devised a workflow that could either work using only heuristics or a combination of heuristics with deep learning, where heuristics assigns most concept mesh code mappings and deep learning assigns some additional mappings on top. Regarding resources, both approaches use two dictionary files that were created by filtering and restructuring Mesh 2021 and SCR. And in the mesh file, only codes belonging to the drugs and chemical category were retained. These files did not completely cover the set of mesh codes present in the dataset, but managed to cover most of it. The heuristics approach started with an exact matching mechanism that leveraged several types of information. However, it still left many unmapped entities, so we tested partial matching using the PyMesh package. Results obtained with this approach were very bad, so we rapidly ditched this component. Alternatively, we augmented the exact matching component by adding complex mappings of entities that had multiple codes from the gold standard training annotations. Concerning the deep learning model, we used SAPBER to obtain embedding representations for the mesh codes in the dictionary. Then, we extracted dense representations for discovered entities and compared these with mesh embeddings through cosine similarity. Finally, a similarity threshold was used to decide which mesh codes should be returned by the model. Here you can see that the deep learning model was only used in 2 submission runs and obtained the highest recall in run 2, whereas the heuristics approach obtained the best performance in run 4. Pretty much every submission was above median and benchmark performances, and please note that these results are influenced by subtask 1, as they rely on the entities detected in previous chemical recognition submissions. Finally, for the indexing subtask, we tested 2 different approaches. The first one was a rule-based approach with a 2-stage pipeline, where we firstly extracted mesh codes from specific parts of the document, such as the title, abstract, captions, tables, and figures. Then, we evaluated the percentage of occurrence of each recognized mesh code in the documents and defined different occurrence thresholds for the different document sections. The second approach was based on TF-IDF and begins by modeling term importance as function of its nonlinear frequency times its rarity. After computing the importance of each mesh code per document, we need to select the most important terms. After some experiments with threshold-based and probabilistic-based selection methods, we opted for a simple threshold-based method focused on precision. This last table shows the results obtained for the indexing subtask, including the results of the 5 official submissions and also of 2 unofficial submissions. Here, we can see that firstly, the Heuristics approach obtained significantly higher performances than the TF-IDF counterpart. Secondly, an improved version of the heuristic system, which provided better results in all dataset splits of the training set, still yielded lower performance in test time than the best official submission, which was run 1. Finally, using a method similar to the benchmark, where we returned all mesh codes present in the title and abstract, except for the dash entity, we still obtained lower recall than the official benchmark, but had higher precision. As some final remarks for this presentation, all models herein presented were developed considering only exact evaluation metrics, and mesh indexing was the hardest task due to error propagation from the first 2 subtasks, and many indexing mesh terms do not exist after the normalization step. In other words, these indexed mesh terms are not mentioned directly in the text. As some possible future lines of work, for the first subtask, we could explore entity reconstruction mechanisms, other model architectures, and also weighted loss schemes. For the second subtask, we could further experiment with the subpart embeddings for normalization purposes and try running this for the full amount of annotations instead of combining it with the heuristics component. Finally, for the third subtask, we could investigate the use of the mesh tree structure to analyze if adding parent-related mesh terms can help in the indexing task. And with this, we conclude this presentation. Feel free to contact us if you have any questions, and check also our research group Twitter if you're interested in checking other ongoing works. Thank you for your attention.
Great. So Zhiyong, I see there are 2 questions for you in the chat. If you can quickly answer them. One question is, did you try training only with provided training restricted to the abstract and training data versus using full text?
Yes, let me answer the question. I'm from the team. My name is Rui. And regarding the named entity recognition part, we used other data sets comprising only abstracts, but in every training, we also added the NLM-Chem data set. So we do not we do not experiment only using the abstracts, but we see improved performance using the all data sets, abstracts data sets on full text, and then doing a training pass only using the NLM-Chem data set.
Thank you. And one follow-up question, can you clarify the difference between how mesh descriptor entries and SCR terms are handled in the normalization?
Yeah, this was part of the heuristics component of the normalization block. The way we structured it was we gave priority to the descriptor entries from mesh because those are curated entries. And after we got it was like a sieve mechanism. After we got a pool of unassigned entries, we combed through those entries and searched for matches with codes from the supplementary chemical records. We did this because we believe that by giving priority to mesh codes, we have a higher confidence of assigning a correct code to the entity. SCR can be seen as quite of an experimental database that must be processed and curated before being added to the mesh validated dataset. the addition of the SCR clearly brought performance improvements in the normalization process. But it was not, let's say, it was not enough to completely cover the spectrum of codes that should be used in this data set that was provided.
All right, thank you. And so we'll move on, and there's additional question you can answer.
Just to answer this quick question, each mesh code has a tree structure, and we went through the tree structure, and we combed through the first parent node, and we used that parent node to filter by the category of drugs and chemicals. That was our main approach to filter relevant codes for our dictionary files.
Great, thank you, Joel. So our next speaker will be Hong-Jae Kim from Korea University. His talk title is Improving Tagging, Consistency, and Entity Coverage for Chemical Identification in Full-Text Articles.
Hi. Can you hear?
Yes, we can hear you. If you can speak a little bit louder, that would be even better.
Okay. Thank you for inviting me and our team as presenters. We are team 139, and my name is Hong-Jae Kim. Our team participated in the NLM-Chem track challenge, task 1, the chemical identification task. The task consists of 2 stages, recognition and normalization. And we are very happy to know that we are the first place in recognition. Anyway, there are 2 common approaches to solve the task. We choose the pipeline approach in this challenge, which trains a recognition model and normalization model independently and combines the models at the inference time. The most important feature of this task is that the data consists of full-text articles, which is different from other common data sets, such as PC5CDR and ChemNer. Therefore, we focus on the characteristics of full text and how to reflect them in the modeling. As a result, we concluded 2 aspects, tagging consistency and entity coverage, should be considered effective in solving the task. First, we should improve tagging consistency. In general, the same words or phrases within the same article often refer to the same concept or entities. Therefore, models should classify the same spans of text into the same one. However, since current models generally use sentence level input, they classify the same entities into different ones, as shown in the figure. This is called the tagging inconsistency problem. We emphasize that the problem should be tackled to improve recognition performance. Second, we should improve entity coverage or recall. The motivation is that different articles have different distributions due to differences in research topics and writing styles, which leads to unseen entities that did not appear during training, but appear at new articles. This tendency is more pronounced when the data consists of full text than when it consists of only titles and abstract. In fact, 48% of entities in the NLM-Chem's test set are unseen, which is much larger than 35% in PC5CDR. In sum, we focused on improving tagging consistency and entity coverage in this challenge. To do so, we propose the following method and techniques. They will be described in detail in the following slides. First, we prepare multiple training data sets. We use the original NLM-Chem data, and additionally, existing data sets, PC5CDR and ChemNer. Also, we generate the new synthetic data, NLM-Chem Syn, by replacing entities in NLM-Chem with their synonyms. Finally, we pre-train our recognition models on different training sources, and then fine-tune the models on the NLM-Chem data. Also, we adapt model ensemble, which means we combine the predictions of different models that are trained on different training sources. Next, we address the tagging inconsistency problem using a simple majority voting method. First, we collect all inconsistent predictions in the same article. We then compute the majority for the predictions and change all the minority predictions to the majority. The figure depicts how the majority voting method works. Finally, we propose a hybrid approach to improve entity coverage in normalization. The motivation is that dictionary-based models usually achieve high precision but low recall due to the limited coverage of their dictionaries. On the other hand, neural network models achieve higher recall but with less accuracy. We attempt to leverage the strengths of both while compensating for the weaknesses of each model. Specifically, we combine a dictionary model and a neural model. The dictionary model first performs normalization based on exact matching between entities and the dictionary. The neural model further performs the process on entities that are not matched by dictionary lookup. These are implementation details of our system. We use the BioLM large model of Lewis as the recognition model, and use CTD and Wikidata as the dictionary, and use Biosyn as the neural model for normalization. We combine 20 recognition models for the final submission. For more details, including the hyperparameter configuration, please refer to our paper. This is the ablation study for recognition models. As shown in the table, transfer learning is effective and it mostly improves recall. Although generating NLM-Chem scene does not require additional labeling cost, it can be more effective than using existing human label data sets such as PC5-CDR and ChemNet. And also, we compared 3 types of ensemble models. First, the fine-tune only model combines single models trained only with the original NLM-Chem data. The second, transfer only model combines transferred models from PC5-CDR, ChemNet, and NLM-Chem scene. The last both model combines single models of all types. As a result, we found that ensemble models outperform single models, and ensemble can be more effective by combining models trained on different sources. Lastly, majority voting consistently improves performance, although it is quite simple. We note that the method is particularly effective when there are many same entities in one article and there is severe tagging inconsistency. This is the ablation study for normalization. The table shows that the dictionary lookup achieved high precision, but it has low recall. Our hybrid model significantly improved the recall, resulting in a higher F1 score. However, maintaining the high precision of the dictionary model remains a challenge in future work. This is our submission result. In recognition, our system significantly outperformed the median and baseline result. And however, in normalization, our systems achieved similar F1 scores compared to the median and performance below the baseline. Our systems achieve high recall as we intended, but relatively with low precision. The cause of low precision may be due to error propagation from the recognition models. This could be alleviated by adapting the end-to-end approach in future work. Also, the performance can be improved by designing high-precision dictionaries. This is the last slide. To solve the chemical identification task, we focused on improving tagging consistency and entity coverage and proposed various methods. In addition, we provide other important experiments and heuristics in our paper. Please refer to our paper for more information. Thank you for listening. If you have any questions, feel free to contact me. Thank you.
Thank you very much for the great presentation. There is one question for you in the chat box. Transformer models are resource intensive and higher performance is possible with ensembles. Applying these methods to the millions of articles in PubMed and PMC is very challenging. So the question is, what would you suggest we consider to achieve high performance with computational efficiency?
Yes, ensemble models, we use the ensemble method for the final submission only. And other method we used, for example, majority voting and transfer learning and hybrid approach are all effective. Yeah, so we recommend all method. Yeah.
Thank you. Thank you again. And then we'll have the next speaker will be our Aslan Aidan Gosselin from Florida State University, and his presentation title is a BERT-based hybrid system for chemical identification and indexing in full-text articles.
Can you see my screen?
Yes, we can see your screen.
Oh.
But
Oh,
yeah.
okay.
Yeah, we can see your slide.
Okay, cool. Hi, everyone. My name is Arslan Arslan. I'm a PhD student from Department of Statistics, Florida State University. Our team number is 128, and my advisor is Jinfeng Zhang. I'm very happy to have this opportunity to present our work in today's workshop. Now, I would like to introduce our BERT-based hybrid system for chemical identification and indexing in full-text PubMed articles. We participated in Biocritic 7 Challenge, Track 2. This track consists of 2 subtasks, chemical identification and chemical indexing in full-text PubMed articles. The chemical identification task also includes 2 parts, chemical named entity recognition and chemical normalization using mesh term. The chemical indexing subtask is to decide which chemical mentions should be indexed for the PubMed articles. Our team built a hybrid pipeline for track 2. Specifically, we applied BERT-based methods for chemical NER and chemical indexing, and the sieve-based dictionary matching method for chemical normalization. Let's get started with chemical named entity recognition. The baseline model was a transformer BioBERT model trained and evaluated on NLM-Chem data set. The result is quite promising with F1 score of 0.803. First off, we experimented with several different BERT-based models, including BERT large, clinical BERT, BioBERT, BlueBERT, SciBERT, and PubMed BERT. We trained and evaluated these models on NLM dataset. In the end, PubMed outperformed other models, and the F1 score improved more than 2% when compared to baseline BioBird model. So we chose to use PubMed as the base model for chemical NER test. Second, we experimented with several different training data sets. BC7 also provided CDR dataset from BC5 and ChemD NER dataset from BC4. We trained models on different combinations of datasets to see if adding more data would increase the performance or not. The first model was trained on only NLM dataset. The second model was trained on the combination of NLM and CDR. And the third model was trained on NLM, CDR, and ChemD NER. Three models were evaluated on the same dataset, which is NLM test set. It turned out that the first model achieved the highest F1 score, which means that adding more data from Biopretive 4 and Biopretive 5 did not improve the NER performance. So we decided to only use the NLM-Chem dataset to train the model. We also fine-tuned the parameters to get the best performance. And next, we also did some error analysis on prediction result. We noticed that a chemical inside a protein should not be annotated as a chemical. For example, glucose is a chemical, but glucose transporter is a protein. To solve this problem, we also trained a protein NER system to identify proteins so that any chemicals inside proteins could be dropped. Then we used a data augmentation technique to further improve the model's performance. Specifically, the first step, we replaced the chemical entities with a random string. For example, we replaced aspirin with a random string. The goal here is to force the model to learn from a context, not only on the word itself. Excuse me. The second step is to randomly select one non-chemical entity and replace it with a random string. The goal here is to reduce the influence of bias introduced from the previous step. We found out that this data augmentation procedure improved the performance slightly. So we decided to adopt this data augmentation method in our pipeline. In the end, we also used AB3P tool to identify abbreviations. In this way, we can expand the mentioned text prior to normalization. Here's the chemical NER evaluation on the final test set. The best F1 score is from round 1, which is 0.86. We are really glad that we ranked the second place in this subtask. In the chemical normalization test, we use sieve-based dictionary matching method. We use several different dictionaries, which are PubDaters, UMLS, Mesh Lexicon, and also we use NLM annotated dataset. We scanned the identified chemicals through all this dictionary in a specific order for 2 rounds. After the first round, we used AB3P tool to expand some abbreviations and then scan for the second round. Here's the evaluation on the final test set. Our best F1 score is 0.81 from round 2. We also ranked the second place in this competition. Okay, subtask 2 is a chemical indexing prediction task for full text PMC articles. We participated unofficially since we didn't submit the result by deadline. We tried 2 approaches. First, we formulated the problem as an extreme multi-label classification problem. The input is a combination of title, abstract, and body text. And the output is mesh term. However, we achieved only 0.42 F1 score on development set, which is not ideal for chemical indexing. So we didn't submit the result at the first place. The second approach is a binary classification system using PubMed BERT with some engineered features. The input is sentences with the chemical, with the same chemicals, and we also appended the section name, for example, method or introduction, and also chemical name before the sentence. And the output is simply a true case or false case. And we achieved F1 score of 0.62 on our development step. Since the second approach outperformed the first one, we decided to use binary classification model for this subtask. And we also trained this model on two different data sets. The first data set is BC7 NLM-Chem data set. And the second data set is PMC data set. We extracted and organized this data set by ourselves. This data set includes 5,000 PMC full text articles. And the title, abstract, body text, section information are extracted from PMC. The chemical names, chemical identifiers are extracted from PubData. And the chemical indexing, we also call it mesh indexing. We extracted them from PubMed. And notice that this is a sentence level corpus. We only keep sentences with chemicals inside it. Okay, here's the result for chemical indexing. Our best F1 score is 0.825 from round 2, and we ranked the first place for this task. Thank you everyone for listening. Please let me know if you have any questions.
Thank you very much for your great talk.
Thank you.
I don't see any questions in the chat or in the, oh, there is one. The chemical indexing task is difficult and new to everyone. Could you share your perspective on the greatest challenges in this particular task? So we're talking about the second task, the indexing task. What are the most difficult part that you found when participating in this indexing task?
I think the greatest challenge when we solve the chemical indexing problem is that the mesh terms are quite large, which means that we have a really large number of labels. If I remember correctly, there should be 20,000 chemical mesh there. So yeah, as I mentioned in our two approaches, the first approach we try to solve it as a multi-label classification problem. So the labels are too many. So that's the reason why we have a lower F1 score there.
Thank you. And quickly, a second question in the chat box. In your first task, which is the identification task, how many percentage of data is augmented?
Oh, okay. So, we submitted 4 runs, and the first run and the second run, they have different percentages. The first one, we use 50% of the data as augmentation, and the second one, we use the 70% as the augmentation data. Yeah.
Thank you. I see there's another question, but to keep up time, I'll let you answer them in the chat box.
Sure.
Thank you as I can. And our next speaker is Virginia Adams from NVIDIA, and her talk title is Chemical Identification and Indexing in PubMed Articles via BERT and text-to-text based approaches.
Hi, can you guys hear me?
Yeah, we can hear you.
Okay. Just let me open the slide. Sorry. Okay, cool. Okay, hello, my name is Virginia Adams, and I'm an applied scientist on NVIDIA's conversational AI team. Today, I'm going to be presenting my and my team's submission to the Track 2 task for entity normalization, entity recognition, and chemical indexing. First, I wanted to start off by giving you guys an idea of the grand vision that we had at the onset of this task. So we thought, instead of having an individual model to do each of these tasks separately with separate parameters, separate architectures, and separate objective functions, why don't we try and take advantage of some of the recent advancements in the natural language processing space and make a unified multitask model to do all of these tasks at once. Specifically, we decided to try a prompting approach or a text-to-text approach where we formulate each one of these tasks as a question that we pass into a pre-trained generative language model, and we have it generate a textual answer that we then do some post-processing on to put it back into the original challenge submission format. So specifically, we tried this text-to-text approach with T5 and GPT. T5 is a sequence-to-sequence model, so it's a encoder-decoder model with a transformer encoder and a transformer-based decoder, whereas GPT is just a transformer decoder architecture. Before I dive into how we turned each one of these tasks into a text-to-text task, I want to go over what we considered our baseline approach that we compared our text-to-text results to. So our baseline model is pretty much identical to what the task organizers gave us at the onset, with the difference that we used Biomegatron instead of BioBERT. So Biomegatron has the additional benefit that it has a biomedical vocabulary, which is specifically important for named entity recognition. And so when the Biomegatron tokenizer was trained, it was trained on PubMed text, which allowed the model to chunk chemical and biological terms into semantically rich and meaningful pieces instead of arbitrarily or going character by character like with the normal BERT-based vocabulary. The benefits of this are twofold. When the NER model is asked to classify each specific token as a chemical or not a chemical, there's just fewer tokens to classify when things are separated more meaningfully. And then also, it's easier to identify a token as a chemical if it's a semantically meaningful piece of the entire word. And here are our results on the test set for named entity recognition using our baseline system. I believe we scored third, I think, overall on this challenge. As you can see, so we tried with BioBERT, and then we also tried with Biomegatron. Generally, we saw that the biomedical vocabulary, as said in the beginning, is more effective than the usual BERT vocabulary. Surprisingly, so we tried with the 345 million parameter models, but we also tried with 800 million parameter and 1.2 billion parameter models and didn't actually see performance increase. In fact, we saw a performance decrease, which I think is just interesting. And our best submission was an ensemble of several Biomegatron-based models that we just did we averaged the probabilities from these models in our ensemble for the final predictions. Okay, so let's talk about how we turned named entity recognition into a text-to-text task. So we basically, we wanted to make the input to the model as human readable as possible because these are language models pre-trained on just general text. They were not pre-trained on domain-specific data. And so we said, what I have boxed in purple here is the input, the example of the input for the NER system. So we said find entities, and then we broke down the full text into sentences, and we passed one sentence at a time into the model with the prompt find entities, and then the next prompt answer, and then we had the model generate the specific, only the text strings answer to the entities in this sentence. So whenever we needed to convert it back into the format for this competition. Of course, the spans are part of the submission file. Originally, we tried having the model predict the spans as well as the text, but found that these models really, really struggle with predicting accurate numerical information. And so we had to, after it predict the string, we had to do some post-processing to do some string matching to find the exact position where the span occurred in each paragraph to then format this in the correct submission format. Here are our results for the text-to-text approach compared to the baseline approach that I talked about previously. Generally, the text-to-text approach is worse than the baseline approach that we found, as shown in our results, but with some caveats that I think are very important. So our best, all of our baseline approaches had biomedical pre-training on PubMed articles, whereas our text-to-text models did not, just due to time constraints. And then also our best models all had a biomedical vocabulary, which again, our text-to-text models did not. And so I feel that this is not a apples to apples comparison, and our text-to-text approach is still very promising. I think this is just our first crack at even trying to formulate this task as a prompting task. And so definitely with some prompt engineering or some prompt tuning or something like that, we could, and in addition to pre-training, I think we could see a significant improvement in performance for named entity recognition. And also so this was specific output from GPT. Was it really that bad? So we went ahead and we looked at the model predictions compared to what was labeled as the ground truth. And we found that GPT, though it would miss some of the specific chemical names that were labeled, it would pull out the chemical portion of gene names and protein names in the abstracts. So it is finding a lot of chemical names that aren't labeled as ground truth because they're not entirely chemical names. And so I just thought that was another interesting point to point out to you guys. All right, next let's talk about our baseline approach for entity linking. For our entity linking baseline system, we used, I know the same as the previous presentation, we use self-alignment pre-training, in which we take an existing pre-trained BERT encoder and we do a second stage pre-training where the new objective is to make chemical entities that are synonyms closer together in feature space, and then chemical entities that are not synonyms further apart in feature space. Here's just a t-SNE visualization that I did where the left-hand side is before we did the pre-training and the right-hand side looked interesting. So it's what we did after pre-training. After doing the second stage pre-training on our BERT-based encoder, we basically took all of the mesh terms and mesh synonyms and put them into an index where the index contains the embedding for each of those terms. And then as we want to do entity linking on any specific test example, we take the cosine similarity between the test example and all of the terms in the index, and then assign it the mesh ID corresponding to the term that had the highest cosine similarity with the test term that we wanted to do entity linking on. So to turn entity linking into a text-to-text task, we framed it very similarly to our NER text-to-text prompt, where we just said normalize entity, and then we gave it the specific entity in the sentence that we wanted to normalize in quotations and context. And then we have just one sentence at a time again. And then we had the answer be what we called the canonical string form of the entity we want to normalize. So once again, ideally, we would have the system predict the specific mesh IDs without having to do some post-processing, but these types of models really struggled with accurate numeric information. And so it was another post-processing step to do some string matching on what the model predicted to then map it back to a real mesh ID. And so here are some examples of output from the model. The top one is the model getting things completely incorrectly, and the bottom one, the model gets it correct. As I've said probably 5 times now in this presentation, whenever the model had to predict, had to generate numerical information, it got it incorrect. And so here's an example of the model trying to predict a chemical name, starting with 2. Okay, sorry, I'm out of time. I can go quickly. So basically, yeah, the predicting chemical names with numeric information was a struggle. And so we ended up just using our baseline entity linking system for our submission. And then here are our baseline entity linking results. I think we got like third to last for entity linking. And so I think that just goes to show there's a lot of room for improvement for both our baseline approach and our text-to-text approach. And then lastly, we didn't actually submit for topic indexing because it was super challenging for us to get correctly. Sorry, this is my last slide. Sorry about that. For topic indexing, we stuck to just a text-to-text approach, and we couldn't fit the entire like article into the input context for either GPT or T5, and so we had to break the article down into a couple of sentences at a time. And you can imagine doing topic indexing with only a couple sentences of an article at a time is not going to work very well. And as you can see, our results were kind of abysmal from that, so we didn't submit for that part of this track. And in conclusion, I think our text-to-text approach is still super promising, but for right now, our best systems were an ensemble of our baseline approach with Biometric. Thank you, everyone, and I'm happy to take questions.
Thank you, Virginia, for the great presentation. So there is one quick question, and also given the time, just make a clarification. Is the vocabulary used in the large biometric models biomedical or general? Because in that slide, I also noticed that the larger model did not perform better than the small models.
Yeah, so okay, so for the larger models, it was general. So that could actually be a reason. So that's actually, I mean, that's an interesting trade-off, right? Like it's a much larger model, and so in theory, it can store more information. But the vocabulary is not biomedical, and it really shows that the biomedical vocabulary is like pulling its weight over just having larger parameters. So yes, the two larger ones used the regular BERT vocabulary.
Okay, and well, given the time, I think we'll stop here. But there is a question in the chat box, and I hope you can answer
sure
afterwards. And I'd like to also thank you and thank you all the speakers for the NLM-Chem track. And this is the end of the first session in the morning. And then now, according to schedule, is the break time. We will reconvene at 11:55. So about 15 minutes, a little bit shorter than 15 minutes break. So
11:15.
Yeah,
11:15.
So please, that's Eastern time. So please come back in 15 minutes for our keynote talk by my colleague at NIH, Dr. Josh Denny. Thank you very much.
Zhiyong, I see Josh.
Hello.
Hello.
Chris, are you
You are live.
Yeah, you're spotlighted.
Okay, thanks. Great.
Turn your camera on. You're up.
Okay. All right. Thanks, everybody, and welcome you to the second session of the first day program of the Biocredit 7. And it is my great honor and pleasure to introduce today's keynote speaker, Dr. Josh Denny, who is the CEO of the NIH All of Us Research Program. Dr. Denny has been involved in the All of Us program from the very beginning. First as a member of the advisory committee to the NIH director, and then served as a PI for All of Us Data and Research Center. Before joining NIH, Dr. Denny was a professor of biomedical informatics and medicine, director of Center for Precision Medicine, and a vice president for personalized medicine at the Vanderbilt University Medical Center. So where he was both a practicing internist and a researcher. So Dr. Denny is one of the first to use electronic medical records and genomics to better understand disease and drug response. Dr. Denny was a leader in the development of pheno-wide association studies, PHWAS, and recently phenotype risk scores. He has served as a PI for Vanderbilt site in many nationwide networks such as eMERGE, PGRN, and Ignite. So for his outstanding contributions, Dr. Denny has been elected as a member for of the National Academy of Medicine, the American Society for Clinical Investigation, and American College of Medical Informatics. So I'm personally very much looking forward to Josh's talk. And Josh, now I'll turn the virtual podium to you.
Thank you very much. I hope everyone can hear me okay.
Yeah, you're good.
Wonderful. Well, it's a pleasure to speak with you today and talk about the All of Us Research Program and what we've done here and what our plans going forward are. I hope that this, I was able to catch a bit of the last session, and it's fun to hear some of the engagement on using NLP type approaches and machine learning to go through text and derive chemical information from reports. We hope to make an analog of that available through the All of Us Research Program, which we'll talk about more as we go through this. So, my focus has largely been on precision medicine over much of the last decade and using a number of resources to get at that problem and help us drive towards better prediction and understanding and treatment around health and disease. And so if we think about a population of individuals, we can have a wide variety of experiences, from health to even if when we have or experience a disease, the way that disease presents can be highly variable. And sometimes the diagnosis eludes us because it's atypical. And that is one of the kinds of things we want to think about with precision medicine. As in addition, we also want to think about drug responses. Any drug we take, we think of having maybe a bell-shaped curve in terms of responsiveness and how we may respond to that drug. But in addition, of course, we can have toxicity, side effects, things like that that we would desire to eliminate or minimize. And sometimes, of course, the drug does nothing or only has side effects. And that's certainly true if we think about treatments for mental health and a number of other conditions. So, as we've thought about how precision medicine has evolved, I just wanted to go to one really landmark study that many of us are probably familiar with, the Framingham heart study, which enrolled a fairly modest, we would say today, number of people, about 5,000 people in 1948. And from this study and others like it, we discovered a number of foundational things. This is actually from the first results-driven paper from the Framingham heart study, in which they showed an association of these really high cholesterols and blood pressures and incidence of coronary heart disease. And you can see that, what was thought to be normal is cholesterols of 300 and systolic blood pressures of 175, had dramatic increases in incidence of heart disease. And we've learned about cigarettes and smoking and exercise and diet all as intervenable risk factors for heart disease from studies like this. And they use custom ways of measuring. And of course, we all know the benefits that have arisen from that. As we think about diseases in genetics, there have been a number of genetic studies, first starting outside of electronic health records. I'm going to jump and zero right into the use of electronic health records. And this is the first genome-wide association study that was performed using electronic health records that discovered something new. And in this case, we were looking at autoimmune hypothyroidism in a network called the Electronic Medical Records and Genomics, or eMERGE network. And each of these 5 sites found cases of people who had autoimmune hypothyroidism within people that had extant genotyping. And they found that the algorithms worked pretty well when you really dug into the records. And you can see the case positive predictive values there, generally over 90%. One site was lower, and that was due to really the need for more NLP that was not executed at that site to really get that algorithm and differentiate it from people that, for instance, had thyroid cancer as a cause for hyperthyroidism. But in general, it worked well, and we identified a new thyroid transcription factor that was associated with hypothyroidism. And so, these kinds of studies proliferated and became commonplace to show that, and so much so that national resources such as the UK Biobank, such as FinGen, Estonia, and of course, the All of Us Research Program have decided to leverage healthcare data as a fundamental part of the resource to do things like these genome-wide association studies. And so, from GWAS and genome-wide association studies, where you're looking at a given phenotype and you're surveying genetic data, and you find genotypes, allows you to think about, kind of the inverse study or phenome-wide association study, where you take a genetic variant or really any other independent variable and look at, the phenotypes that can arrive from, we'll say, electronic health records. It really can be beyond that. Almost all GWASs today would be based on structured information from things like ICD codes. It could also be things like surveying across all survey results. But you can also imagine using natural language processing and laboratory data, and some groups have looked at that as well. And so the idea is you go from the genetic variant as your independent variable instead of a dependent variable, and can look across phenotypes. And this is primarily done in electronic health record formats. I just want to focus on this as one example. This is using data at Vanderbilt, looking at electronic health records. And at the time, we had 37,000 people in which we had enough data that we could impute HLA types. So human leukocyte antigens would be drivers for the immune system and our immune response. We know they're associated by class with a number of autoimmune diseases. And here we have about 100 or so associations that replicate a lot of known associations between given diseases. Mostly in this case, we're seeing autoimmune diseases and the phenotypes and a given HLA types by class. And so you can see the ones mostly in the bottom in HLA-DPA1, what we call the class 2 are associated with a number of phenotypes, and some different phenotypes than our HLA A, B, and C, which are class 1. Notably, you see a few new associations in here as well, and really can replicate about 40 years of HLA biology with a single study of only, I'll say 37,000 people, only because these cohorts are growing so large, and it can let us explore these kinds of things. But as we've done this, there's a real problem with our genetic studies out there. They're not very diverse. This is true really for a lot of science, randomized controlled trials, things like that as well. If you look at the genome-wide association studies, which are perhaps the easiest to really quickly assess this for, you can see the vast majority are of people of European ancestry. And when you look at the next block, Asian, most of that is driven by East Asian, South Asian, or Southeast Asian are much lower in representation. If you think about the US population, that non-European, non-Asian, 4% there, it represents more than a third of the US population. So that's a real opportunity in the United States for us to leverage the diversity of this country to help tackle this problem and create more equity in the representation of genetic studies. This has a real impact on us. So if we think about using and doing genetic studies here, one of the things we're really excited about, for instance, you could be things like genome-wide association studies we talked about, which identify genetic variants. And if you don't, we do see different loci in different populations. Sometimes those lead to medications. The most recent class of anti-lipid agents is derived from a small population of individuals. Originally in the Dallas Heart Study, about 5,000 African-American individuals who had a higher burden of loss of function variants in PCSK9, which has led to a successful treatment there. We also think about things like polygenic risk scores, and you can see on there that you have a really tight confidence interval for this polygenic risk score in European ancestries. But when you look at other ancestries, the predictive accuracy falls off quite a bit. So how do you make those really work in different populations? And then on the bottom right, the interpretation of genetic variants. And all these variants here on the bottom are variants that have been called pathogenic, in part based on their frequency in individuals of European ancestry. And so in this case, we're talking about people getting implantable cardiodefibrillators, real significant interventions. But you can see that some of these variants, like that first variant, occurs in 27% of individuals who self-identify as Black in the United States. And so clearly that cannot be a pathogenic variant. So what's happening is people are getting interventions they don't need, based on really inaccurate data underlying it and not having diverse enough data behind that. So as we think about the tools we use to, what I'll say, dissect individualized health, it's much bigger than genomics, surveys, and EHRs. If you start with things like Framingham, you get survey instruments and exams. You overlay things like genomics with lots of studies that have gone over time, a more modern method looking at health records. But there's lots of other kinds of information we have here. And certainly in this conference, you guys think about the breadth of the health record and getting into clinical text and things like that. And in fact, that's the kind of thing I started with in working with text, and then moving to full text records to identify phenotypes, looking at drug response and things like that. And really getting at the richness of these different elements, then pulling in things like mobile health technologies, and then really thinking about things like social determinants of health. Some of that's geospatial linkages, but it can also be derived from other methods as well. And then getting things like imaging data, of course, has become hot as we think about deep learning methods and the things that we can derive from imaging data that's really emerged into what even doctors recognize, such as estimating age or blood pressure from a retinal scan. As we think about the All of Us research program, our mission in light of what we know is to accelerate health research and medical breakthroughs to enable individualized prevention, treatment, and care for all of us. We think of this as having three components. Starts with nurturing relationships for decades with at least 1 million participants who reflect the diversity of the US. We want to deliver one of the largest, richest biomedical data sets and make it broadly available and secure. And we want to catalyze an ecosystem of communities, researchers, and funders who will make all of us an indispensable part of health research. And so we launched in May of 2018 publicly. And since then, we've enrolled over 400,000 participants. From those participants who are consenting, 305,000 completed all the basic steps. 320,000 have given us biospecimens. The minimum of that is DNA. I'll talk more about that later. And about 250,000 electronic health records. And you can see that we were enrolling at a pretty good clip until COVID-19 forced us to pause in March of 2020. And before that, we were enrolling about 3,000 people a week. At that point, most all of our efforts to bring people fully in involved an in-person visit. And so we had to come up with new ways of reaching people in a more contactless way. And you can see that as we've started back in later 2020, but more significantly in 2021, we're starting to pick up again with both digital enrollment and doing things like sending saliva kits to people so they don't have to come in to a visit if they can't or don't feel comfortable doing so. I mentioned that we really focused on diversity, and that's really been a key part of the program from the beginning. We have enrolled people from all 50 states, the states and US territories. The states that are darker represent places where we have healthcare centers that are funded and enrolling participants. Overall, over 80% of our participants are underrepresented biomedical research. Typically, that's through, that's a number, actually usually more than one category. Race and ethnicity is one that we focus on, and more than 50% self-identify as a race or ethnicity other than white, non-Hispanic. And you can see the age distribution there. That broader metric includes sexual gender minorities, socioeconomic status, and other categories such as rural location. So what kind of data do we collect? People can come and participate in a number of different ways and sign up online or through their smartphone. Right now, it's you must be 18 years or older. It's a video consent process, and it includes authorization to share electronic health records. Essentially, no matter how you come in, you share the same kinds of data. We have a number of surveys that participants fill out, sort of hopefully seeking to combine some of the best items of things like a more traditional study with knowledge that we should be collecting other kinds of information, such as electronic health records. So focusing on surveys on things like demographics and habits and maybe family history and healthcare access, social determinants of health, stuff like that that you don't necessarily get from electronic health record in depth. We also launched a survey on COVID, which dealt with a number of aspects, not just whether or not you had COVID, but the experiences around it, financial, social distancing, optimism, anxiety, activity, a number of different aspects there. We have a brief set of physical measures, and at that appointment, we also would collect biosamples. You can see DNA, RNA, cell-free DNA, serum, plasma, saliva, if not blood. We have certainly increased the use of saliva over COVID-19, and any given week, 20 to 40% of our samples could actually be saliva samples. But majority of the people are still donating blood and a richer set of specimens there. And then we also have the ability to connect in your own devices. And here's an example of sharing Fitbit data or Apple Health Kit data. And about 20,000 people have connected devices to the program. You know, I say this is just an example of one of the kinds of things we could do. We realized as we were enrolling people in this time retrospectively, as COVID-19 hit, that we could go back in these 3,000 people per week, essentially, that were coming into our clinics and enrolling and look to see whether or not those individuals had COVID. So we designed a dual antibody technique to go look and identify people among those 24,000 people that enrolled from January 2nd to March 18th of 2020, really early in the pandemic. And you'll recall, we had just a couple dozen cases in March at that time, and look for potentially new cases. And we identified 9 cases, 7 earlier than known in 5 states. You can see Illinois, Massachusetts, Wisconsin, Pennsylvania, Mississippi. And our earliest case was January 7th, which is before the earliest case in the US, and really points towards, since these are serology tests, towards a case in December or so. And you can just see the earlier case here that we identified. One of the things that I think makes our study unique and is because, as I'll talk about a little bit more, we have a cloud-based model for research. And so the idea is bring the researchers to the data. And so the study that we did on antibodies, you can access through this URL. If you are a approved researcher, you can get the very data set, the very analyses. And we hope this becomes a model for really making fair kind of research, findable, accessible, indexable, reproducible research easy on the platform. And so anyone can come borrow this, adopt it, reuse it, etc. We also have a number of core values in the program, one of which is participants will have access to their information. And this was a real opportunity for us to engage in that, as COVID testing and potential COVID exposure would be of interest to people. And so we put those on our dashboard. If you were one of those 24,000 people we tested, you got a notification, you can come in and see whether or not we identified COVID antibodies or SARS-CoV-2 antibodies in your blood at that time. And of course, reminding you when you actually donated blood as well. This is an example, of course, without detection, since that's the vast majority of the people. And as with everything, we support it with information resources if needed. So another thing we're going to be returning is genetic information. Right now, we're currently returning non-health related traits like, do you taste cilantro, what kind of earwax you have, and genetic ancestry. And about 60,000 people have viewed those kinds of results. We're also working on generating health related genetic traits that people can have back. So things like hereditary cancer risk, or like the example I talked about before with cardiovascular disease. Those are kinds of things we return, and those all have actionability with them, as well as pharmacogenomics. In both of these cases, they are supported by the website information, descriptions, sheet that you can send to your physician, and genetic counselors that are available to both talk you through the results and for questions that you might have later on. And we plan to launch this later in 2022. I alluded to this earlier. Now I'm going to shift to talking about how researchers use the data in some of the use cases, and then some of the use cases we anticipate in the future. So, a traditional research approach, of which I participated in many, including until recently, such as the UK Biobank, is, you bring the data to the researchers. You have a central resource whereby a validated researcher can go and download the data. You might vet their resource locally before you approve it. And then the researchers download it, use it in their environment. It requires them to have, of course, the necessary compute facilities on premises, and also has a consequence of limiting security really to the weakest link and what happens at those sites, and limits our ability to audit, which means that other controls are put in place. Our approach, and is becoming pretty commonplace, is a cloud-centric approach where people come in and use our sources, which democratizes access. But in this case, it also allows us to take what's actually pretty sensitive data and make it available to more people faster. One of the things I'm really excited about in the cloud is an idea that you all are familiar with, but the idea of using this to give someone like what we consider a passport access model, because we can control access and secure access better, is a way that we think we can accelerate research. As researchers come in, all these data from 350 enrollment sites, from more than 50 EHR uploaders, which themselves are amalgamations of other sites, those data all come into a raw data repository. We use, of course, common protocols on how data are collected. We do a number of data curation steps, including things that fire as the data are uploaded at the site, as well as we employ some privacy methodologies and centralized QA and QC on the data. And then there are a number of different data tiers working from the bottom up. We have a public tier, which anyone can access, databrowser.researchallofus.org. You can go now, it works on your phone or desktop, and you can see things like the basic elements of the kind of EHR data we have and things like that. Then moving next, what's available now is the registered tier, and that's at a level of de-identification that exceeds HIPAA safe harbor standards. And so that includes survey data, EHR to physical measurement data, and some Fitbit data. From there, we look to release a controlled tier, which will include more information, notably genomics. It still has obvious PII removed, but it's got real timelines. It does not, it's not de-identified at the level of safe harbor or an equivalent. And it's where we will eventually put either extracts or derivatives of clinical narrative data, or allow access to that. And we expect other things to come in available in there. The first real notable difference will be some more granularity of the data and genomics. And those are all accessible through our researcher workbench. And then over time, we'll allow access to biospecimens and participant data. I wanted to get a little bit lower level and a little bit more detailed here. And so our healthcare provider organizations, those entities that are right now uploading full electronic, or they're uploading the structured electronic health record data mapped to OMOP data formats. We have designed the process and our agreements with the sites to be able to expand that to narrative data. We'll consider longer term things like registry data and imaging data from EHR sites as well. We also look forward to adding data centrally. It's actually some of this theoretically easy stuff like the death index, when you talk about the scale and the type data that we're using, has actually been a little harder to work through, but we think that we'll be able to come up with access models. It's a balance of the access model and the protection and how the data was originally collected. But we look to bring in more kinds of centrally added data, and with the control tier, we'll have our first kind of geospatially linked data at a high level, and we'll look to release more over time. And then participants can also do their own participant portal-based FHIR uploads, and that is mediated through some of our participant portals that are used on our side, and then they can link and share that, or through the Apple Health Record feature. I mentioned earlier, people are doing surveys, they're uploading their Fitbit data, stuff like that as well. And so just a brief overview of the kind of EHR data. Epic is the most common vendor. We have 16 different vendors that are currently represented, and some of these sites have had different vendors over time as historical data they're uploading. You can see on the right, we basically are just mapping out quality is progressively green metrics, and you can see generally that gets better over time, as you might expect. But as new sites come in, sometimes numbers go down, and we work to make those things progressively better as defined through OMOP quality metrics. I mentioned the program launched in May of 2018, but as we get electronic health record data, it is a consent for all the data that they have at their sites. So, our surveys started in 2018, or a little bit before that, given our beta phase. But the EHR data can go back to the 1980s. As you can see, our Fitbit data goes back to 2010 or a little bit before. And so a lot of people have a lot of longitudinal data there available for in silico analyses. And you can see just kind of the breadth of some of those numbers as we accrue these data. And this is all the data that's available right now. I talked about the public data browser in brief. This is what it looks like. You can search across EHR data, survey questions, other components, and there's a QR code there to kind of dive into it and see. And this is designed to help you just get a very basic sense of whether there's enough participants there that might have a given condition or drug exposure, things like that, to do a potential study. And then when you want to do an analysis, you apply to the researcher Workbench. This is that central cloud resource. It was launched May of last year. And it is, I mentioned that passport access model. So it all operates as non-human subjects research currently. So when you're approved as a researcher, you come in and describe your work in a workspace model. You don't need to get any separate IRB or project approval. And so essentially a researcher that is from a site that's already signed on as a master agreement, a new researcher can get started in an hour or two of training in the process, and then they have access and can create new projects on the fly with the data. Right now, in our current phase of access, access is limited to people that are affiliated with U.S. nonprofits. We are actively looking to expand that internationally and for profits as well. Since we launched, we have about 1,200 researchers that are using it, about 800 active projects. The publication count is at least 21. We update that periodically. More than 240 institutions have registered, including 24% from HBCUs, HSIs, or other minority serving institutions, including other nonprofits such as patient advocacy groups. And you can see we're representing a diversity of states in there as well, including Puerto Rico. I'm just going to talk about an example of a few things using the data and studies that have been done. So this was one of the early papers that was published on All of Us. It looked at a predictive algorithm for patients with glaucoma that would need surgery. The algorithm was originally designed at a single site. That site, when they brought their models from that site into All of Us, their machine learning models performed with an AUC around 0.5. So, not really different than random chance. When they retrained models using the really, I'd say the diversity of the site data across all of us, you can see the AUCs got significantly better with the random forest model there approaching approaching 1. One of the things that I think this is important about, and I think we all recognize in machine learning space, is the importance of having a diversity of data to train on. And that diversity includes, of course, participant diversity, but it also includes things like areas of the country and insurance plans and EHRs underlying and providing the data, because all these things can filter in and create biases in the data, as we all know. And I think that's one of the things that I think all of us can provide for folks as they build such models. I want to give another example, and this is an example of a PhD student of mine. I was on his committee. I was not a chair of his committee at Vanderbilt, and he developed an algorithm that used gene expression data from Zhiyong to identify drugs that might lower cholesterol. He also looked at blood pressure, and he found a number of drug candidates, and then he took those 69 drug candidates and screened them through electronic health record data at Vanderbilt. And as is not surprising, a number of the statins were demonstrated the strongest LDL effects, as you can see on the right there. And that's what we would expect. He identified some others which might be new signals, some that actually raise raise cholesterol as well. And so in the discussion, the question came up, oh gosh, this took you about 3 years, your PhD, and you've done this at one site at Vanderbilt, can you replicate that? And many of us have been in the place of like, well, gosh, yes, I have this result and I'd like to get another site. And that's hard to do. That often takes a long time to go through this. And then you have to get the site to go do it. And that was part of the Emerge network for a number of years where we tried to do this. And that was generally pretty hard. What he did is he said, okay, so this was in April of 2021, this year. And he applied for the first time to all of us. And about a week later, from his application, he sent me this figure. So, from kind of start to finish, he was able to replicate these results in all of us and get, good figures that he could include in his paper. And essentially, he found that the algorithms, both models using OMAP, could port with just minimal changes in the algorithm, basically adapting for places where Vanderbilt had been changed or modified, things like table names and things like that in OMAP. So I think this is the kind of story that we're excited about, to show that you can adopt and adapt and replicate results in a big resource. So I want to talk a little bit about where we're going and then give you an example of kinds of stuff I think that the resource will support. So we're launching the control tier in genomics in this winter. We expect it to be about 90,000 whole genome sequences and about 130,000 arrays. More than 40% of that population will be diverse by race and ethnicity. Of course, even higher when you consider the other metrics. And it'll have a lot of other data in it. You can see about 4,000 people, for instance, will have everything. They'll have whole genome data, Fitbit data, and other components here. And that will be, I think, a rich resource for people. We have a number of web-based tools to look at this. And you can see in the web-based tools here, you can do things like you can pull in diagnoses and medications and patient demographic or survey answers, as well as things like, who has whole genome data. That helps you build a cohort that you can then analyze using Jupyter notebooks and R or Python. And this just gives you a sample of using a notebook to do a GWAS, using Hail and Plink, which are commonly tools, and a FEWAS built on our alpha phases towards launch, just showing some of the stuff we expect to see in this case, looking at a FEWAS of a known variant that influences diabetes and puts you at risk for it. And you can see what you expect to see there. And now I'm just going to talk a little bit about a future use case of this. And so one of the things I think, if you go back to the initial example of interpreting a genetic variant and knowing whether it's pathogenic, we have the ability to take a given Mendelian disease and translate that disease to things like human phenotype ontology features, and those can be mapped to features in electronic health records. And this is some of the work that's been done in my lab at Vanderbilt and here at the NIH now, and continuing at both places. And so a use case that I think all of us will enable. And by using those terms and maps from things like ICD 9 and 10 codes to PheWAS codes to human phenotype ontology, you can create a risk score, and you can weight that risk score by the information gained of each of the features. And then you get an aggregate score. So it works like this. We take 3 hypothetical people. In this case, we're looking at cystic fibrosis. Cystic fibrosis has a number of features in it. And things like bronchiectasis have a higher import and weight than asthma, because asthma is much more common, bronchiectasis. And so you get aggregate scores. And these aggregate scores let you differentiate cases from controls based on just the features of a disease. And you need to use that because, not all these people, especially with rare diseases, will be diagnosed with a condition. And that's kind of what you need if you're, looking at unknown variants at the time. And right now I mentioned that we're just using ICD codes, but I know for a fact some of you have worked on ways of mapping full text to conditions like HPO terms. And so it could be built up on ways like this, and it could be a powerful resource to actually translate the EHR data and the genetic variant data, pulling the 2 pieces together at the same time to actually have clinical impact. And so here's an example. This is not using genetics, where you can see that you can use all of us in a demo phase with the data we currently have by phenotype risk scores to differentiate to conditions like cystic fibrosis or hemochromatosis, sickle cell anemia in these cases. The red being cases, the aqua being the controls. And here's an example using a small number of people from the eMERGE network, which I talked about before. So this is 23,000 people. The redness represents the degree of pathogenicity. The numbers represent standard deviations from expected. And these are all known pathogenic variants. So this basically shows, yeah, we're getting what we expect to see. The vast majority of them are, more than 2 standard deviations from expected. And, some look worse than others. And that's probably notable too, because not all variants are created equal. But, what's really powerful is when you start looking at variants that are unknown significance, then this is what we get tons of when we sequence. And so here are all variants we don't know whether they're pathogenic. And you can see that a number of these actually look pretty pathogenic. And one of them is 7 standard deviations from expected. And then one of these on the other side, though, looks protective. This tuberculous variant here actually, doesn't look like it's a risk variant. And, you probably shouldn't assume that you need to do something different here. And so this is the stuff that I think we can start to see coming out of this as just one example of the kind of work that is from informatics to clinical impact. And so just to remind people where we are, we're very near to this winter launching the genomics and control tier. That initial control tier will still be structured data, but we're looking very forward to building in and bringing in other kinds of data, such as narrative data in the future. At this point, I don't have a timeline for that, but it is something that we are building out as part of our 5-year plan of the kind of data that we will be bringing into the resource. And I also mentioned that we're going to be returning health-related genomic results as well. So with that, I'll thank you all and I appreciate the time and happy to address whatever questions we have time for.
Thank you very much, Josh. This is very exciting. We do have questions for you. And the first question is, how do you envision text mining can contribute to all of us? What specific tasks would be most useful?
Yeah, I think we will seek to bring in multiple levels of textual data, and that will include things like radiology, pathology reports to full text clinical notes, discharge summaries, those sorts of things that people have available. So really all those will be valuable. It could start with things like one of the things we did at Vanderbilt that was pretty valuable was, for instance, even identifying people who had clinical genetic tests to see, what people had. Clearly that can be helpful for phenotypes, especially rare diseases. So I mentioned, some genetic diseases, but things like adverse reactions like osteonecrosis from bisphosphonates, a common medication used for osteoporosis. You can't really find that through billing codes. It's the kind of, you go mine the EHR, looking for reactions to, vaccines, for instance, or understanding what people might be having from like symptoms of long COVID. I think these are all kinds of things. So text mining could help. So understanding the records, mapping specific diseases, looking for drug responses, and then mining things like radiology and pathology reports for the basic structure and concept representation are all fair game amongst many, many other types of projects.
Great. And just to follow up on this quickly, and I understand there are some type of text data already available, like survey data already available in all of us. Can you talk a little bit more about that?
So the survey data right now that's there is structured. The textual data in the surveys as we release it and just sort of verify that it will be de-identified is really very short answer. Probably there'd be some components perhaps of mapping text to things like diagnoses, but probably the more exciting text mining approaches will be as we bring in clinical data, and that will probably be in various stages.
Thank you. And another question, do you know if the research on long COVID could be organized through All of Us platform or a similar one?
Yeah, I think if you look at the resources out there, the big EHR resources that have COVID participants or patients in them, I think they're right now all based on structured data, unless you're working at a given institution. And I do think that you can use these data to look at long COVID. I think it will be both through things like survey data in some cases, as well as the EHR data, looking at lab results and diagnoses that happen post, you could look at vaccine events, you could look at the diagnoses as well.
And another question, thank you very much for your interesting talk. They have a question, the person has a question about data security. What kind of strategies are you using to prevent potential misuse of data, like personal genetic data?
Yeah, so first is, we have a centralized environment and we actually don't let you download the data. You need to do the analysis in our platform. Part of it starts with knowing who the person is, so identity verification as part of that. And then using the environment, we actually have some controls on looking at data exfiltration as well. We understand you're going to have to pull out, for instance, the image you create, but for such as a graph or table or that kind of thing. So do the analysis there, describe your project, of course, do all the, sort of, if you're familiar with FISMA and that kind of stuff that we do on the architecture and penetration testing and white hat hackers. But for the most part, it's around knowing who the person is, having to describe that, and having the ability to audit it. And essentially we trust users through the education process and description of what happens. Anyone can look at the workspace descriptions and flag a workspace for review. And we hope through that process that it's sort of something we can go have conjoint trust in the process and visibility to protect the use and thereby enable greater use as well.
And this is probably our last question. Would you consider organizing a shared task to sort of jumpstart use of All of Us data for disease-specific task?
That sounds like a great idea. I think you should consider starting that, and we would be happy to support it.
Great. Well, thank you very much, Josh, and I'm sure that our audience are very excited about All of Us data, and I'm sure they'll probably reach out to you if they have additional questions.
I hope so. We need all of you to come in and make it useful, because it's a platform, not a project.
Thank you very much.
Thank you.
Thank you. Now it's about 1 minute before our schedule, so I'm now turning to the chair of the track 3.
Hi everyone. So welcome to the task 3. My name is Davy Weissenbacher and I will be the chair for this session. So the goal of the task was to extract the medication name in the tweets. And we will have the overview presentation of the task that will give the description of the data and the performance of the system, followed by the winner of the task.
Can you start the presentation, David? Sharing your screen? Sorry. Can you share your screen?
Yeah, I can do that.
Just so we have.
But I will play a video because that's easier to do. So we can start actually. So desktop, and I'm going to the video and playing the video. Let me know if there is any issue with the video when it's running.
We cannot hear anything.
David, you need to select the sound from the computer in order for us to hear.
When you open share screen, Davy, on the bottom left, it'll say share computer audio. You got to check that box.
You're trying to read it. Here it goes.
I'm a research associate at the University of Pennsylvania, and in this presentation I will give an overview of the task 3 run during the BioCreative 7, where the goal was to extract the medication name position in the tweets. A timeline of a Twitter user is the set of tweets that are posted by this user over time. So here is my Twitter account as an example, where I'm using Twitter to communicate with my friend, speaking about my taste of food, my research, or my activities, my hobby, playing video games. And among those different tweets of different topic, sometimes I may tweet about the drug that I'm taking. So the goal of the short task was to find the tweet that are speaking about drug and extract the name of the drugs inside those tweets. This task is often the first step into larger epidemiologic studies that want to use Twitter as a source of information. As far as I know, this is the first work that tried to extract the name of the drugs in the timelines. So the corpus that we released during BioCreative was pretty unique in that sense. There have been some work done which focused mainly on trying to get the corpus containing the tweets mentioning the drug names. And the main techniques used by the previous works was to use lexicon to match the entries of the lexicon in a large set of tweets. This technique has a big bias, which is that you will not find the tweets that mention the drug name that are not inside your lexicon. So you will miss a lot of drugs names in Twitter. You will also miss the drug names that are misspelled. So the drug names are inside your lexicon, but in Twitter, it's most likely that they are misspelled. Like for example, here, olopatadine, you would expect an E because that's the real name. And you will also find a lot of false positives, so tweets that are not related with drug names, but captured by the match of your lexicon, like all the tweets that are speaking about Lyrica, which is a singer, but also an anti-epileptic drugs, or Propel, which is a verb in English. Among all the tweets that are mentioning drug names are pretty rare, with only 0.2% of the tweets in our corpus that we will describe in the next slides. So the challenge of the BioCreative was pretty hard in that sense because of the imbalance of the positive tweet that mention the drug names and the negative tweets that are not mentioning a drug name and speaking about other topic. We use a standard definition for our task where, given a tweet, The goal was to extract the beginning position and the end position for each of the drug names mentioned in the tweet. We use a tabular separated value format to release the data to the participant, where the first column was the tweet ID, the second column was the text of the tweet, the third and the fourth was the beginning position and the end position of one of the drug name mentioned in the tweet. The fifth column was the span extracted at this position, and the sixth column was the drug name normalized. So for example, here in this tweet, that was a plural form, so the normalized form just was the singular form. For each tweet that do not mention any drug name, the last column remain empty. And for the tweets that mention multiple drug names, like here Hydros and Moltrin, we duplicate the tweets and we wrote the position of one of the drug name for each duplication. We define drugs as the drugs in general, plus the mixed products and the dietary supplement. To correct the timelines that were used in BioCreative, we listen keywords from the Twitter streaming API. So those keywords were related with pregnancy. So for example, here pregnant. And we use a classifier to find a tweet that mentioned self-declaration of pregnancy, like I'm 3 months pregnant today. Once we have identified a tweet that mentions a pregnancy, we use the Twitter API to correct all the available tweets that were posted before the tweet announcing the pregnancy by the user. And we continue to correct the tweets that were posted after the tweet announcing the pregnancy. So that constitutes our big database of Twitter that we assume being pregnant. And from this data set, we extracted randomly 212 user timelines for annotation. So a human annotator annotated the pregnancy time frame, so from the beginning of the expected beginning of the pregnancy to the end of the pregnancy, and all tweets that were posted 1 month before and 1 month after the pregnancy time frame. We have two annotators that double annotated 12 timelines, and the inter-annotator agreement was pretty high with a 88 Cohen-Kappa score. As usual, we split the corpus into two sets, the training and the test set. We randomly selected the tweets, so that means that the tweets posted by a user can be either in the test or in the training set. The corpus exhibits the real distribution of the tweets, so very few tweets that are mentioning a drug names and a lot of tweets that are about another topic. So that means that the corpus of BioCreative is highly imbalanced, which is still a challenge for machine learning based system, because they will tend to overgeneralize and consider the positive tweets as noise in order to improve and optimize their loss function. To help the participant training their system, we release an extra data set, which was initially released in 2018 during the SMM4H competition. So this data set was collected using 4-week classifier that we applied on our database of timelines. We randomly selected around 12,000 tweets for annotation. And as you can see, those tweets are, this corpus was balanced with almost the same number of positive and negative tweets. And this corpus was interesting in the sense that all the negative tweets that were in this corpus were mentioning nouns or phrases that were ambiguous with name of drugs. We also release the code of a baseline extractor that were published in 2021 during the AME conference. So our extractor was based on a BERT standard embeddings, followed by 2 layers of bidirectional LSTM to label each of the token of the tweet using the IO schema. We train our BERT system using first undersampling. So we just took all the tweets of the balanced dataset SMM4H and we train the BERT system on that. Then we fine-tune the system on the tweet of the training set of BioCreative that were classified as mentioning a drug name by an existing classifier that we have also developed. So that means that the BERT only see at this stage the true positive and the false positive made by the classifier, and we fine-tune the system on that. During the prediction time, we took the test set of the BioCreative and we again applied the classifier. All the tweets that were filtered out by the classifier were said to not mention any drug names. So that's a hard decision made at this level. And all the tweets that were mentioned as, that were classified as mentioning a drug name were given to our model for extraction, and the model extract the name of the tweet inside, the name of the drug inside those tweets. Our task was well attended with 65 teams registered and 60 teams that submitted a round at the end of the competition. So we organized the competition as follows. We split our dataset into training, validation, and extra dataset that were released in March 2021 for the team that were registered early. Then in September 15th, we released the test set. The participants have 4 days to compute their prediction on the test set and to submit their prediction. We only kept the best run for each of the team that submitted a submission. And we ask the submission to be submitted to the website Codelab, which has an automatic way to run the evaluation script on each of the submitted prediction. If you are interested by the task, the post-evaluation is still running and will not be stopped on Codelab. So you can ask us the dataset, train the system, and submit your prediction on Codelab, and you will get the results without seeing any, without seeing the gold standard. We evaluated the performance of the system competing in the shared task using standard metrics, the strict and the overlapping precision recall and F1 score for the positive class, because our dataset is very imbalanced, which in our case is the detection of the span of the drug name. The difference between the strict and the overlapping F1 score is in the strict evaluation, we reward a system only if the system is able to find the truth, the span annotated by the annotator. So he needs to find exactly the span to be counted as correct. Whereas in the overlapping evaluation, we release this constraint and we reward the system as long as the system is able to find at least one part of an annotated span. So in that case, the system will be counted correct because it detects arnica, which is a part of the right answer, arnica balls. This graph details the performance of the best system submitted by the participant. As we can see, the performance are pretty high for the top rank system with strict F1 score that are above 80%. And we have 4 systems that beat the baseline system, so there is some improvement during this last year. And we have the two best systems that have obtained the same F1 score, which is possible given the few number of positive examples in the test set. So we have to make the difference between them using the overlapping F1 score. Here is the median between the system without counting the baseline. Most of the systems make the choice of transformer-based neural networks for making their prediction, except one which use lexicon. Looking at their description, it's still unclear which type of embedding should be used as an input, with the top rank system making very different choices regarding the corpora used to train the embedding. Some use a general domain document to pre-train the embedding, such as BERT or the Megatron, whereas some other use BERT and train on biomedical articles. The genre also is very different, with some using a corpora, embedding trained on a corpora very similar to the test set, the tweets, whereas others choose research article. On the other side, the architecture seems to be a little bit more clear, with the best architecture being an architecture with two loss function trained, one loss function focused on detecting the tweet that mentioned the drugs, and one loss function focusing on extracting the position of the drug name. With the first system using a classifier apply first on the data, and then a question answering system to extract the span of the drug in the tweets that has been filtered in by the classifier. So the same architecture than the baseline system. Whereas the second system was using a multitask network, with one part of the network detecting the tweets mentioning the drug, the other one was extracting the location of the tweet. So this shared task, we observe improvement in the performance of the system, and that was mainly due to the heuristic used by the participant to improve their training despite the imbalance of the training dataset. To do so, the most common technique was to use data level preprocessing, where some of the negative tweets were removed from the training dataset, and or positive tweet added to the training dataset. The participants also combine, in general, the data level preprocessing techniques with the ensembling techniques, where the prediction of multiple machine learning systems are combined to make a final decision, which in general improve over compared to the decision of only one machine learning system. Only one system used a loss function that was tuned to have a different weight. How do they find the negative tweets? The participants use the existing lexicon, and they only took for training the tweets that mention the entry of their lexicon, or they use classifier to filter out the tweets that are not likely mentioning drug names. So that was the strategy used by 6 systems. They also often combine the negative, so removing the negative with adding positive tweets. To do so, only 2 systems use oversampling, which consists to duplicate existing positive example in the training set. Most of the participants used data augmentation using the SMM4H 2018 corpus, which was balanced, or creating a silver dataset using lexicon or using a lexicon or classifier to find the tweets that are most likely mentioning drug names, and use those tweets as new training examples. And some system also use data generation, where this time existing tweets mentioning the drugs are modified, so substituting the name of the drugs in the existing tweet by other name of the drugs, so that you obtain new tweets that are mentioning different name of drugs. The name of drug can be from the same category or from a different category of drugs. We have seen that. We have seen both strategy used by the participant. Distorting the existing tweets by removing characters, removing words as well, or also using external tools to paraphrase an existing tweet mentioning a drug, or for translating the tweets into a language and translating back into English and use the translation back as a new training example. To conclude this overview, the BioCreative Share Task 3, which aims at extracting the name of the drugs on Twitter, was a pretty popular task with 65 teams registered. During this share task, we released 212 timelines annotated with drug names, a corpus pretty unique, and a corpus which was pretty challenging as well because it has the natural distribution of the tweet mentioning drug names on Twitter, an event which is pretty rare. To improve the training of their machine learning system, despite the class imbalance of our corpus, most of the participants combined two strategies. The first one was to filter out negative tweets using lexicon or classifier, and adding in their training examples positive tweets by selecting real tweets or generating new tweets that contain drug names. The top rank system performed pretty well with 84 strict F1 score, a score that is getting closer to the score obtained by name entity recognizer when they are trained to recognize common name entity on Twitter, such as name of people or name of organization. If you are interested by this share task, you may also be interested by the coming share task organized during the SMM4H in 2022, where we will have 8 share tasks on different language using Twitter, of course, and also review of WebMD. So stay in touch with us if you are interested to register in this competition. If you have any question, do not hesitate to reach through my email or through my tweet, and I will be open for questions. Thank you.
And I will be indeed open for questions. So
I think there is a question in the Q&A, Davy.
Yeah, all right. Have you also considered doing something similar for Google search data? I'm not very familiar with Google search data, so I would say no. For the moment, we haven't. We have considered other sources of information, such as Reddit or dedicated post in forums, but that's all what we have in mind for extending this research. Any other question?
There is a question in the chat. I can read it for you if you want.
Mm-hmm. Yeah.
It says, will you consider any normalization work in the future?
Yes, that would be an interesting task. We have some part of the data, and that will be interesting because, of course, the way that the people are describing their drug, the misspelling as well on Twitter. So we need to have some kind of normalization to be able to pinpoint in the lexicon which drug the Twitter user was actually referring to. So that will probably come at some point.
Okay, there's another question. How would the results needs to be in order to be useful for some application?
It depends which type of application you want. In general, I would estimate, but that's just my opinion, but I would estimate above 80, above 55 would be starting to be useful for further application. But the further application can be also with a human in the loop correcting the information, or fully automatic. Then in that case, you may have different expectation from the output of your system. But 80, 85 start to be pretty useful, because you find most of the drugs that you're looking for, and most of the drugs found are not too noisy. So you can start to trust a little bit the system, and this is the performance that we start to see with from the best system in this competition, with 80 F1 score. Which
also important in that realm is that it can process a large data set quickly enough. So processing time is key. Otherwise, you can have a really great performing system and you just cannot run it at the volumes that are needed. And Davy smiles because it did happen to us that the best performing system couldn't. So he came up with something that was a little bit more, a little bit, not so much hit on performance, but it was much faster to run. So we do have studies already where we're using it. So particular intake of specific medications in pregnancy, and we need to find amongst all the timelines that we have, which are like over 100,000 or so, mentions of medications that these women are taking during pregnancy. And so, so finding, for example, in this case, it was beta blockers and calcium channel blockers. So we have already some practical uses for a system like this.
Yeah, and the system that Grazia was referring to is the baseline system. So the baseline system was built to go fast in order to be able to process billions of tweets in a reasonable amount of time. There is another question. Will you start collecting data on processing speed? You mean evaluating the process, the speed of the process?
Yes, other evaluations in BioCreative have actually collected data on processing speed as one of the interesting metrics.
Yeah, you're right. We should have done that.
Yeah,
I didn't think about it.
It's one of my main requirements at this point, because we did find that close to when we needed it, that it wouldn't run. I don't remember the exact speed, but it was not doable. It was like a 3-month run for all the billions of tweets that we have. So, so it is a key thing. So particularly when you have big data like social media.
Yeah. But I can tell you straight away from the architecture of the system that I have reviewed, they will probably not be very fast, because they are ensemble of BERT, which take times in general, even for inference time. So I would not expect them to be very, very, very fast.
It might be interesting to re-rank as a post-competition, like take that into account and then publish like that. I mean, it will give some, perhaps somebody else, some other team bragging rights there.
All right. So if you have any other question for me, I will be, you can send it to me by email. To stay on time, we will start with the next presentation with you. You are here. Do you want to do it live, or do you want to read the video?
I will present live.
All right.
Okay,
then
I'm sharing my screen.
The floor is yours.
Okay, can you see my slide?
Yes.
Hello. Okay. Hello, everyone. The topic I'm sharing is NCOS ASGS, detecting medication names in balanced Twitter data with pre-trained extractive QA model and data-centric approach. NCOS ASGS is our team's name. I'm Zhang Yu from National Central University, Taiwan. Okay, this is the outline for my sharing. I will first describe the challenges of the task and our strategy, and then the detailed introduction of our system. And the last part is about the internal experiment results and our evaluation results. Okay, for the introduction part, I will explain the task, challenge, and our strategy. In Biocreative 7 Task 3, the participants have to develop text mining systems to extract the spans of the drug and the dietary supplement from the given tweet. Here is an example. There are two main challenges. First, the distribution of the medication names in the tweets is very sparse. The training data has about 89,200 tweets, but only 218 tweets contain at least one drug name. And second, the limited length of tweets make it difficult to disambiguate the word sense from context. For example, the painkiller and the Botox can be used as the cultural product names. Okay, to tackle these challenges, we followed up the strategy of the previous research, namely the baseline system. And our changes, although the same two-stage approach was used, we made some changes. First, we transformed the NER problem into extractive QA problem, which yields better results. Second, we applied multiple pre-trained language models, such as BERT, DiBerta, Splinter, for experiments. And third, data-centric approach was used to augment the training data and enhance the quality of external data set. Okay, in this section, we will introduce our system, which consists of three parts. The first part is our medication text classification component. We will introduce the pre-trained models used here. The second part is about extractive QA component. And the last part, we will describe our training data set and our data-centric approach, which is used in the above two components. This picture shows the overview of the fine-tuning process of our two-stage system, combining tweet classification, extractive question answering, and the data-centric approach. Okay, the first part is about tweet classification. In this section, the model classifies tweets as whether they contain drug names or not, as positive or negative. According to previous studies in social media mining for health, classification methods based on pre-trained language models like BERT are shown to have the high performances. And we think the effectiveness of different pre-trained language models is influenced by the pre-training corpus and its special model architecture. If a pre-trained corpus is more similar to the text of its downstream task, it will have better results. Therefore, we surveyed the related literature and the experimental reports to select the following pre-trained models. The first one, BERT, pre-trained on large amount of tweet text. And the second one, DiBerta, is a state-of-the-art model on glue leaderboard, which pre-trained on common domain corpus. And the last two model, BioBERT and BioElectro, shows good performance on tasks like biomedical question answering. Okay, For model training and inference, Google Bird's architecture is employed. CLS token is used as a feature. We then appended a softmax linear layer to output the logits of positive and the negative. But here, we also concatenated the promoting sentence. This tweet mentioned a drug, medication, or dietary supplement in it, and each tweet as an input. This table shows the boosting effect of adding promoting sentence when fine-tune for a trait-based model on these two different training data. Yeah. Okay, the second part is about extractive question answering. In this part, the model needs to select the spans of drug names from the given tweet, which is classified as positive in the first component. The previous study demonstrated that replacing sequence labeling with extractive QA can encode entity context or keywords into the query or question. Therefore, the attention mechanism can utilize information for the entity extraction. So we use the extractive QA instead of the usually used sequence labeling approach. We made the query extract the spans that mention a drug, medication, or dietary supplement in the tweet from the task description page of the BC7 task 3. And we use the splinter as a model to extract the spans of the drug names. This picture is from Splinter's paper. Splinter's architecture is the same as BERT, which uses multiple layers of transformer encoder components, but it uses the pre-training method shown in the picture called recurring span selection. This pre-training method masks the recurring spans, and the model needed to select the spans from the previous passage. This behavior is very like the task in the extractive question answering dataset, like SQuAD. Yeah. So Splinter is shown to perform best on almost all SQuAD-like datasets of different fields, especially when the sizes of training set are small. And following the instructions in the Splinter paper, we appended a question token to the end of the input sequence in fine-tuning. In the output layer of the model, Splinter computed a start vector and an end vector of the question token through using the parameter matrix S and E. Each token's start and end position probabilities are calculated by these two equations. We use the word-based searching as a post-processing method to extract potential multiple drug names in a tweet. Each candidate span was filtered by a threshold value of probability. Okay, the third component and the last component is our data-centric approach component. This approach was proposed by engineer in a workshop this year. He emphasizes the importance of label consistency of the training data. And we consider that data-centric approach can be divided into two parts. The first part is for data augmentation, which focuses on collecting more relevant or generating more similar data for training. And the second part is about data quality enhancement, which focuses on orientations such as label consistency or data filtering. We think data-centric approach could achieve greater performance improvements when when the task is with few cases or imbalanced labels. Yeah, in our work, we found two data quality problem, and I will explain these two problem detail in later slides. Many researchers have previously conducted studies on the topic of tweets and drug usage, and some of them have published corresponding data sets. Hence, in addition to the data set provided by the task provider, namely the number 0 data set, we also collected and processed the following 4 additional data sets to fine-tune the classification and extractive QA task. And for number 4 dataset, because the rule matching approach used in this dataset is not as accurate as expert annotation, we did not use the dataset directly, but used it as a supplemental source after filtering it with bird tweet classification model trained with other 3 datasets. Okay. And we found 2 types of label inconsistency, namely the data quality problem in the external dataset. The first is we found 343 extracted drug names for social media mining for health 2018 task 1 could not be matched to the corresponding tweet. Here's one example. We should notice the brown color positions. The alphabet order is different from the tweet sequence and the annotated drug name. Yeah. And the second problem is the inconsistent character length of extracted spans among datasets. We found that the average length of drug names in social media mining for health 2018 is longer than the training data set. And we found that here are 3 examples. Some annotated spans contains not only the drug names, but also some additional information. So our solution is we use edit distance-based algorithm and manual correction to correct these mistakes. And then for inconsistent character length, we delete non-essential parts and leave only the drug names. Yeah, just like this. It's before the correcting, and this is after correcting. Okay, this part is about our internal experiment results. The classification performance of each model and the external datasets are shown in this table. We can say that bird tweet model, especially the large version, performed best. I think this is expected since bird tweet is the only model that has been pre-trained specifically on the Twitter corpus. And the large version has more parameters and will outperform the base version. And we can also say the boosting effect of adding external data sets, especially the number 0, number 1, and number 2. Okay, this is the result of the performance of span extraction on the development side. We only send the data labeled as positive by classification model to the Splendor model for drug extraction here. And I think this experiment results demonstrate the higher performance by using the Splendor. Okay, next part is our evaluation, configurations, and the results. Okay, this slide describes our configurations of submitted runs. The model shown in this table are used as the classification models in our second run and the third run. Yeah, in the first run, we only use the bird tweet large model, which achieved the best F1 score on development data set, and use a splinter extraction. Yeah. And for second round, we used all 7 classification models and filtered the tweets classified as positive by at least one model for span extraction. In addition, we also use the medication name dictionary from the baseline method provided by the task organizer to exclude data for which none of the tokens or selected spans belongs to the dictionary. The lexicons of medication names in the dictionary were tokenized by spaces. In the third round, we used a similar method as the second round. The only difference here is that we use majority voting, for example. Okay, the table here shows our evaluation result. We can say that the strict F1 of our 3 rounds all above the mean score. And I want to note here that our recall score performed generally better than the mean score. Yeah, I think this may be related to the application of the 2-stage approach.
You need to conclude.
Okay, I need to complete it. Okay, the first is our discussion. I think all the F1 scores of our 3 submissions exceeded the mean score, and we found that our performance on the development data side and the test data side is different. There is a large discrepancy. So we speculated that the classification models overfitted the development data set. And in future work, we would like to find ways to overcome the overfitting problem. And we hope to be able to achieve good results with just one single model. Yeah, without relying on ensemble methods. Okay, thanks.
Thank you for the presentation, and thank you for the participation as well. Do we have any question? So I have seen some in the chat. Does the Q&A model share the weight with the classifier model?
Sorry, can you repeat?
Does the question and answer model share the weights with the classifier model in your system?
No, the 2 models are trained separately and the weights are not shared. Yeah, but I think it's a direction to do experiments to say whether share experiment or multitask learning will be better.
Yeah, that will be the architecture of the next system. I have a question. Why do you need to have the prompt sentence in front of the original tweet inside during the classification? What is the improvement allowed by this prompt sentence?
Yeah, our experiment shows a slight improvement when we're adding the prominent sentence. We speculate that this effect is because of the attention mechanism. When we add some keywords like drug or medication names or data receipt, the bird, the transformer, the self-attention mechanism may compute this part, and this make it easily can recognize some drug spans in the tweet.
All right, thank you. Do we have any other question? No. And in that case, thank you very much.
Thanks.
And Dongfan, are you here?
Yeah, I'm here.
Perfect. Do you want to live present or do you want the video?
Yeah, let me share my screen. I can present live. Yeah.
All right, perfect. So the floor is yours.
Thank you. Can you all see my screen?
Yes.
Okay, great. Hello, everyone. This is Dongfang Xu. Thanks for inviting us to share our participation in BioCreative Share Task Track 3, Medications Detection in Twist. And this is a joint work between me, my colleague Zhiyong Chen, and my postdoc advisor, Dr. Timothy Miller. So I will skip some of the slides since the share task organizer already described the share task, what it is all about, and some examples of the medication detection tweets, and some characteristics of social media data. I think we all understand how large the social media data could be. And the data set statistics, I will also skip this part. So I will directly talk about our system. So first, for the pre-processing, we first use the open source tool NLTK tweet tokenizer to tokenize each tweet into tokens. So as a hashtag is a single token after tokenization, we further split the hashtag into hash sign and it's following a text string. So the reason we do that because we found some of the example in the training data that the part of the hashtag are annotated as medications. So to reduce the noise of social media text, we replace our URLs with the token URL and our user mentions with the add user placeholder. Lastly, we remove the special characters that cannot be recognized by the word piece tokenizer from the Hugging Face transform libraries. So the reason we do so is that because we found that when these special characters, they can confuse the tokenizations and make some mistakes for the offset. So when we get the results, we cannot align the original. We cannot align our output with the original sentence. So this is just for the post-processing, yeah, to reduce the alignment issues. So after the tokenization, we're using the BIO tagging schema to generate the labels for each tokens. And for the data accommodations, we explored two different techniques to increase the data. So the first one is that we pre-processing the existing data from the social media for healthcare 2018 share task. So this task is a binary classification task aims to detect whether the tweets contain drug mentions or not. So the data set used in this task includes randomly selected tweets and manually balanced with 4,097 tweets containing drug mentions and 4,647 tweets without any drug mentions. So the elective tweets in the 2018 dataset typically contain ambiguous mentions that can be confused with medication. So I think the share task organizer also mentioned that part. So here's some examples of the elective tweets. So all of them contains ambiguous mentions that have the same textual strings as the medications. So the annotation of this data set only contain binary labels, and the extracted drug names, which is showing in this column. So such extracted terms does not always match the drug mentions in tweets because of some lexical variance. So to handle these issues, so we further conduct exact and partial string match to find the offsets for these mentions. The second augmented dataset comes from the extracted tweets we extracted using the Twitter API. So we first collect the top 200 frequent drug mentions from the 2021 and the 2018 datasets as the keywords. We then extract 1,000 tweets for each of these terms from Twitter. As we found that the majority of these tweets in the 2021 datasets have fewer than 128 characters, we remove the tweets that are longer than 120 characters. We further use the self-training framework to select the examples with the most confident drug spam predictions. So specifically, we fine-tuned the bio-ready birth based on case models on the 2018 dataset and the 2021 dataset, and then use it to generate predictions on our extracted tweets. So one thing to be concerned is that these extracted tweets still contain the same drug mentions as in 2018 and the 2021 datasets. So to handle that issues, we manually annotated the use categories for the above top 200 drugs. So including pain, heartburn, birth control, cold, etc. use categories. And we then collect 326 similar drugs in total belonging to the same use categories from the internet. So for each one of these 326 drugs, we randomly select 4 tweets from the above 77,000 tweets whose drug mentions have the same use categories, and we replace their original drug mentions with the new drug terms and get a expense for these 4 tweets. So after removing the duplicate tweets, we eventually obtain 1,194 tweets. So by doing this, we hope that we could increase the coverage of different drug mentions, but also maintain a similar distributions of drug use. So we implement multitask learning models that tackles the text classification and the sequence labeling jointly. And the Phylo loss functions for the models is the sum of the loss from binary classifier and the loss from the sequence labeling classifier. We hope that jointly training models can better leverage the context information for sequence labeling classifier. So to improve the performance over individual models, we apply an ensemble techniques just like all other teams. So I will skip descriptions of all these individual models. So after fine-tuning these models on tweets, we aggregate the outputs from the above 8 models and select the predictions that have been agreed upon by multiple models. So it's basically a majority voting ensemble techniques. So the exact numbers, like how many of the system agree on, is a hyperparameters we tune on development dataset. So for instance, the outputs for ensemble 5s are agreed upon by more than 5 individual models. So for the implementations, we adopt the Hugging Face PyTorch implementation for training our models. We keep the default hyperparameters as in transformer libraries and fine-tune the models with 10 epochs, 64 batch size, and 128 sequence learns. We explored 3 different data compilations. The first one, 2021 plus 2018 plus actual tweets. The second one, 2021 dataset plus the positive example from 2018 dataset and the actual tweets. And the third data compilations are the combinations of 2021 and the 2018 datasets. So this is the results on the data sets. So the 2021 data sets. So to understand the effects of the model initialization and the data augmentations, we present their performance of different models. So firstly, we can see that 7 out of 8 models trained on 2021 plus 2018 plus actual have better strict F1 scores than models trained on the other 2 dataset combinations. So specifically comparing using or not using the ambiguous examples from the 2018 dataset, so without using the elective examples from 2018 datasets, so we find that the ambiguous elective examples from the 2018 dataset improve the precision for 6 out of 8 models. And comparing with or without using extra tweets, So we find that our actual extracted tweets improve the recall for 7 out of 8 models. And in terms of model initialization, we find that on-case models have better average ranks than the case models. So which indicates that ignoring the case information is helpful for medication detections in tweets, especially on models pre-trained on the general domain. We also find that models further pre-trained on biomedical text are helpful for the task, most likely because the biomedical terms are good signs for detecting drug terms. We also compare the performance of ensemble system against each individual system. So without any surprise, ensemble system achieve much better performance than each individual one. And the performance gap of the ensemble system fine-tuned on different data combinations are much smaller. So this indicates that the ensemble system techniques are less sensitive to the different data combinations. We select the ensemble system with the top 3 highest F1 scores as our system submission on the test set. So ensemble 6 fine-tuned on 2021 plus 2018 plus actual. And the round 2 is the ensemble 5 fine-tuned on 2021 plus 2018 plus actual. Round 3 is the ensemble 5, but fine-tuned just on 2021 plus 2018. So our best scores come from the ensemble 5 fine-tuned on all the data combinations, which is the 2021 plus 2018 plus actual. And it has a 4.6 points higher than the baseline system and 10.6 points higher than the average score of all other participants. We also conduct an ablation analysis to understand the effects of multitask learning. So we select the 2 best individual models and train them with or without multitask learning. We find that jointly training the text classifier and the sequence labeling classifier achieve better performance on each task than train them separately. So this is all about our work on biocreative shared task track 3. Thanks for listening. So if there are any questions, I'm happy to take them now.
Thank you very much. That was a good presentation. Is there any question? Yes. I know. Oh yes, no, there is a question coming. Yeah. So I have found that PRMS trained on such imbalanced social media dataset have somewhat unstable training dynamics if using default fine-tuned hyperparameters. Do you find any such issues with your own model training?
Yes, so we did find such unstable issues. But so when we increase the data size, like using the augmented data set from 2018 and the extra extracted tweets, we find that using more data sets, the performance will be a little bit more stable than original one. And we also find that using the multitask learning framework can also mitigate such unstable issues as well.
Okay. I have also a question. In the way that you are combining your ensemble, you are putting, so you are just checking how many of them are agreeing with each other?
Yes, exactly.
Did you think about you just using a weight for also trying to find which model is actually performing better and assigning on the validation set and assigning this way to try to leverage a little bit the uncertainty?
Yes. We do like try that ideas, but so due the limit of time, we don't have like a time to run that part experiment. But we do like that ideas.
Okay.
Yeah,
that's good. All right. So more to come. Is there any other question in the chat? Nope. So if there is no more question, then I will thank all my participants for participating in my task. That was an interesting challenge, and I'm pretty happy with the result. Grazia, do you want to say any word of conclusion as well?
Sure. Thank you very much to all the participants, and thank you, Davy, for organizing. I know it was a tremendous effort to put it together. And I look forward to future iterations of this and future work, particularly that post analysis on processing time. So thank you so much also to the rest of the BioCreative team. It is great to be back and to be part of the organization of shared tasks, which I always promote as something that can move science forward. So thank you all for participating.
Just a quick announcement is that tomorrow we start a little bit early. So if you remember, the program starts at 9 EST US time, so Eastern time. And the other thing is all the works, although we saw some of them here today, all of them are in the proceedings. So don't forget to check there, all the proceedings. Thank you, everyone.
Right. See you tomorrow.
Bye.
Bye.